Subscribe to the channel so you don't miss any videos. What if everything you thought you knew about planets was wrong? We live in a universe where we believe we've mapped the essentials. Planets are made of atoms, composed of protons, neutrons, and electrons, what physicists call baryonic matter. But what if there were worlds out there that defied that fundamental assumption? Planets that are invisible to our telescopes, undetectable through traditional methods, and composed not of atoms, but of something far stranger. Something not even found on Earth. Imagine a planet made not of stone or gas or ice, but of dark matter itself. This is not science fiction. This is the edge of theoretical astrophysics. And tonight, we go deeper than ever before. You're about to enter a realm few dare to explore. A place where the very fabric of matter breaks down and new kinds of worlds emerge. Non-baryonic planets. Hypothetical, yes. But impossible? Not even close. And the implications, they shake the foundation of everything we think we know about the universe. So let's fall into the dark. Let's chase shadows. Let's trace the shape of invisible worlds. To understand the idea of non-baryonic planets, we have to dismantle our assumptions. Right now, everything around you, the device you're watching this on, the air you're breathing, your body, the stars overhead, all of it is made of baryonic matter. Atoms. The familiar stuff. Yet according to our most precise cosmological observations, that only accounts for about 5% of the total content of the universe. Let that sink in. 5%. The rest? About 27% is what scientists call dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it. We can't touch it. But we can detect its gravitational influence. It's out there, forming invisible scaffolding across the cosmos. And we've known this for decades. But here's where it gets wild. What if dark matter isn't just a background player? What if, under the right conditions, it could clump together, form structures, even planets? Now we're no longer talking about shadows. We're talking about something concrete. Non-baryonic planets, celestial bodies composed not of atoms, but of non-baryonic material. Think of them as ghosts with gravity. And yet these ghost planets might be massive. They might outnumber baryonic planets. They might even be hiding right under our noses. The idea sounds outrageous at first. But science thrives on questions that challenge the norm. And the moment we ask whether dark matter can form planets, we open a door into one of the most exciting and least understood corners of astrophysics. So how would such planets form? And if they exist, what would they be like? Could they host life? Could we find them? Could they, in fact, find us? These aren't idle questions. To begin to answer them, we have to understand what non-baryonic matter really is. We've already said it's not made of atoms. That much is clear. But that doesn't mean it's nothing. In fact, dark matter might consist of particles more massive than anything in the standard model of particle physics. Candidates include WIMPs, weakly interacting massive particles, hypothetical particles that only interact through gravity and the weak nuclear force. Then there are axions, sterile neutrinos, and even stranger possibilities like dark sector particles, particles that interact with each other, forming a kind of dark chemistry, entirely separate from our own. Think about that. A parallel realm of matter, invisible to us, yet potentially just as rich in complexity. And if those particles can interact with each other, even weakly, then over time, they could clump. And if they can clump, they could collapse. And if they collapse, they might form something that looks a lot like a planet. Not to us, maybe, but to something else? This raises a tantalizing possibility: parallel planetary systems, drifting through the universe, completely undetectable to us, unless we look in the right way. But let's go deeper. Let's imagine the early universe. Just after the Big Bang. The first fractions of a second. At that time, the universe was a hot soup of particles. Baryonic and non-baryonic matter both emerged. But as the universe expanded and cooled, they began to behave differently. Baryonic matter interacted with light. It formed atoms. It cooled, clumped, and began to form stars and galaxies. Non-baryonic matter, like dark matter, didn't interact with light. It didn't clump in the same way. But it did form massive halos, gigantic structures that surrounded galaxies, dictating their rotation curves and gravitational behavior. What if, in some regions of space, dark matter didn't just form halos? What if it formed tighter structures? Dense, cold clumps, like seeds of invisible worlds? Computer simulations suggest it's theoretically possible. Under specific conditions, dense pockets of dark matter could gravitationally collapse. They wouldn't look like Earth. They wouldn't even look like Jupiter. But they'd have mass. They'd have structure. And crucially, they'd have gravity. Gravity doesn't care whether it comes from baryonic or non-baryonic matter. It just pulls. So picture this, a rogue world, drifting between stars, invisible to telescopes. Not because it's too far. Not because it's too dim. But because it simply does not emit or reflect light. It's composed entirely of particles we cannot detect directly. But its gravity tugs at nearby objects. It warps the light of distant stars. And if it passes near a baryonic planet, it might disturb orbits. Or worse. Could such worlds exist within our own galaxy? Almost certainly. Could one be passing through our solar system right now? That depends on whether you're ready to confront the terrifying scope of what we don't know. The implications don't stop at physics. If non-baryonic planets exist, then the definition of what a planet is would need to evolve. Right now, our official planetary definitions, like those set by the International Astronomical Union, rely heavily on observable characteristics. Mass, orbit, shape. But if something can't be observed directly, does that mean it's not there? Not necessarily. Some of the most crucial discoveries in astrophysics have come not from what we see, but from what we infer. We've discovered entire exoplanets just by observing how their gravity affects the stars they orbit. We've mapped invisible galactic structures by watching how they bend light from objects behind them, a technique known as gravitational lensing. So, in theory, if a non-baryonic planet were to pass in front of a star, we might detect a subtle warping of light. A telltale gravitational fingerprint. That could be our only clue. But what would such a planet be like in detail? That's where things get weirder still. A non-baryonic planet wouldn't have a crust. No atmosphere. No surface you could touch. It wouldn't have oceans or mountains. Not in any familiar sense. But it might have density. Structure. Perhaps even internal dynamics shaped by dark sector forces we don't yet understand. It could be as solid as iron, or as diffuse as fog. It might be 10 times the mass of Earth, or more massive than Jupiter. The possibilities are endless, because we don't yet have a working dark matter particle model. But that doesn't mean we're in the dark forever. The coming decades of astrophysics may revolutionize our understanding of dark matter. Experiments like the Large Hadron Collider and dark matter detection labs buried deep underground are pushing the boundaries. Satellite missions like Euclid and the James Webb Space Telescope are helping map the invisible. And every time we find a discrepancy in gravitational behavior, every time we find something that doesn't add up, it might be a whisper from one of these invisible worlds. So the next time you look up at the night sky and see nothing but darkness between the stars, consider this. That darkness might be filled with planets. Not barren rocks or swirling gas giants. But cold, silent, ghostly spheres of pure non-baryonic matter. And they may outnumber us. To understand the idea of non-baryonic planets, we have to dismantle the foundation of planetary science as we know it. Every rock, gas cloud, star, and biological organism that we've ever encountered is made of baryonic matter. This term, baryonic, refers to particles composed of 3 quarks, protons and neutrons, the building blocks of atoms. These atoms bind together to form molecules, and molecules form everything in the observable universe. But here's the twist. Baryonic matter accounts for only about 5% of the universe's total mass energy content. 5%. The rest is a ghost. Roughly 27% of the universe is made up of something called dark matter, and 68% is dark energy, A force that we still know almost nothing about, except that it's expanding the universe at an accelerating rate. Dark matter, the mysterious substance that doesn't emit light, doesn't reflect it, and doesn't interact with electromagnetic forces, is the prime suspect in our exploration of non-baryonic worlds. If baryonic planets are made of things like iron, silicate, hydrogen, or methane, things we can see, measure, and interact with, then non-baryonic planets are made of, well, we don't entirely know. But that's what makes this so captivating. Picture this: a planet orbiting a star like our Sun. It doesn't block the star's light when it transits. It doesn't reflect the star's light. It doesn't glow in the infrared. It doesn't tug the star enough to be detected via Doppler spectroscopy. But it's there, gravitationally. We can see its influence, its pull on nearby objects, the subtle lensing of light from background stars as it passes between us and them. These gravitational fingerprints are how we've identified entire halos of dark matter surrounding galaxies. But what if those fingerprints could also belong to something more local? Something planet-sized? Some theoretical astrophysicists have proposed that clumps of dark matter, under the right conditions, could gravitationally bind into massive, planet-like structures. These wouldn't be planets in the traditional sense. No rocky crusts, no atmospheres, no magnetic fields, but they would have mass, gravity, possibly even structure. And if dark matter is composed of weakly interacting massive particles, or WIMPs, then these objects might be composed entirely of those elusive particles, bound together not by electromagnetic bonds, but solely by the invisible hand of gravity. But it gets stranger. In theories involving axions, another dark matter candidate, these hypothetical particles could condense into macroscopic quantum objects, like Bose-Einstein condensates, on planetary or even stellar scales. Imagine a world not governed by chemistry, but by quantum physics. A silent, cold, ghost planet drifting through space, unseeable by any telescope, and yet exerting gravitational influence like a whisper through the cosmic dark. Now imagine a solar system where these ghost planets are interwoven among the visible ones. They don't reflect light, they don't emit heat, but they tug, slightly, on orbits. Maybe that's why some planetary orbits don't quite match predictions. Maybe that's why some spacecraft experience tiny deviations in their trajectories, phenomena like the Pioneer anomaly. Maybe we've been brushing up against the invisible. But then comes the question, how would such a planet form? Traditional planets form from accretion. Dust gathers in protoplanetary disks, clumps into planetesimals, then into planetary embryos, and finally into full-fledged planets. But dark matter doesn't interact like that. It doesn't clump electromagnetically. It doesn't stick. So for dark matter to form planets, there has to be a different mechanism, one governed purely by gravity, and possibly quantum mechanics. One model suggests that non-baryonic mini-halos could have formed in the early universe. Right after the Big Bang, regions with slightly higher densities of dark matter could have begun to gravitationally collapse. Without the need to radiate heat like baryonic matter does, these dark matter clumps might have stabilized early and never evolved into stars. Instead, they could have hovered in a kind of suspended animation, massive enough to warp space-time, but invisible to light. And if these structures persisted, could some have ended up in orbits around stars? Could they have even acquired thin shells of baryonic matter, forming strange hybrid worlds, dark matter cores wrapped in a veil of normal material? Think of the implications: a planet that looks perfectly normal on the surface, but whose gravity betrays a much larger mass than its appearance suggests. Astronomers might observe such a world and scratch their heads, thinking, "Why does this planet weigh 10 times more than it should?" The answer might lie beneath the surface, not in iron or nickel, but in non-baryonic matter. Then there are even more exotic theories. What if there are mirror matter planets, worlds composed of a hypothetical form of matter that mirrors our own, where every particle has a mirror counterpart? Mirror matter could interact gravitationally but remain completely invisible otherwise. If it exists, there could be mirror stars, mirror galaxies, even mirror Earths, parallel to ours, but forever out of reach. We're not just dealing with physical speculation here, we're also grappling with the philosophical implications. What does it mean if planets exist that we cannot see, detect, or interact with in any conventional way? Could life evolve on such worlds? Probably not as we know it. Chemical life depends on electromagnetic interaction. But if there's any form of self-organizing complexity in the dark sector, it might be unimaginably different from anything we've conceived. And here's where we dive deeper. Non-baryonic planets may not even be rare. If dark matter outweighs baryonic matter by more than 5 to 1, then statistically speaking, there could be far more non-baryonic planets than baryonic ones. Our telescopes may be looking at only a small sliver of the cosmic inventory, the luminous tip of an unimaginably vast, invisible iceberg. Entire planetary systems could be hiding in the dark, orbiting stars we've never seen, or drifting freely in intergalactic space, forever cloaked in silence. And yet, we are not entirely blind. There are techniques that allow us to detect the invisible, gravitational lensing, for instance, where massive objects bend the light of more distant sources. In rare cases, the lensing signal might reveal not a star, but a planet-sized mass with no visible counterpart. Some microlensing surveys have hinted at strange, unexplained mass distributions, like whispers from dark, hidden worlds. Then there's the tantalizing idea that dark matter might occasionally interact with baryonic matter in rare and exotic ways. If certain kinds of dark matter particles can annihilate or decay, they might emit faint signals, gamma rays, X-rays, or neutrinos. Experiments like Dama/Libra, XENO and LUX Zeppelin are attempting to catch such interactions in ultra-sensitive underground detectors. While none have conclusively confirmed dark matter detection, the search is relentless, and every day, the data grows. And it's not just physicists looking underground or deep in space. Theoretical cosmologists are simulating the early universe with increasing precision, using powerful computers to model how dark matter might have evolved. Some simulations produce intricate webs of matter, cosmic filaments and voids, with clumps that could correspond to non-baryonic planet mass objects. The idea is gaining traction. Still, it remains hypothetical. There is no confirmed non-baryonic planet. Not yet. But consider this. Before 1992, there were no confirmed exoplanets either. The first discoveries were met with skepticism. Now we know of thousands. The unknown only stays unknown until it doesn't. And one day, we may look back and realize the dark matter wasn't just a cosmic background, but a stage filled with invisible actors. Planets, stars, even entire civilizations made not of matter like ours, but something older, colder, and quieter. We've only begun to ask the questions. And now, we go deeper into the strange mechanics of how such worlds might work, from dark gravitational harmonics, to the thermodynamic properties of invisible mass, to the possibility that some non-baryonic planets could exist inside our own solar system. Something is there, and it is massive, but it's cloaked in a veil that no telescope can pierce. These are not illusions. These are not data errors. These are signatures of objects so foreign, so alien in composition, that they resist our most sophisticated instruments. And if we follow that trail of gravitational breadcrumbs, we begin to entertain one of the boldest possibilities in theoretical physics, that entire planets, maybe even entire solar systems, could exist entirely outside the spectrum of baryonic matter. To envision such a planet, strip away everything familiar. No atoms. No chemical reactions as we know them. No molten cores, no rocky surfaces, no swirling gases. Imagine instead a sphere of dark matter, perhaps made of weakly interacting massive particles, WIMPs, axions, or other candidates still hiding within the equations of advanced physics. These particles, unlike baryons, do not interact via the electromagnetic force, which means they don't absorb, emit, or reflect light. A non-baryonic planet could pass through a beam of light like a ghost, and we would never know it was there unless it brushed the fabric of space-time just enough to whisper its presence through gravity. Gravity is the only reason we know dark matter exists. It pulls galaxies into shapes they should not naturally form. It binds clusters of stars tighter than they would otherwise hold. It creates gravitational lensing effects, arcs and rings of distorted light from background galaxies, that betray the presence of unseen mass. This same invisible force might one day lead us to the first confirmed discovery of a non-baryonic planet. Consider the dynamics of formation. In our current understanding, planets form from the accretion of gas and dust in a protoplanetary disk around a young star. The disk is composed of baryonic matter, so naturally, the resulting planets are too. But dark matter doesn't clump in the same way because it doesn't experience friction or heat the way baryonic matter does. Instead, it forms massive halos, diffuse, spherical distributions of mass that extend far beyond visible galaxies. Within those halos, could there be enough density in some regions to create gravitational wells, to pull dark matter particles into a loose but coherent structure? This is where the conversation enters speculative but scientifically informed territory. Theoretical physicists have postulated the existence of compact dark matter objects, dark stars, dark matter cores, and even dark galaxies. Non-baryonic planets would be the smaller cousins of these ideas. They wouldn't necessarily have solid surfaces or atmospheres, and they may not conform to our ideas of spherical symmetry. But they could exist as gravitationally bound conglomerates of non-interacting particles, orbiting stars or black holes just like conventional planets. What makes the idea so compelling is not just its scientific novelty, but its implications. If non-baryonic planets exist, then they vastly outnumber the planets we can see. In a universe where dark matter outmasses visible matter more than 5 to 1, the potential for unseen planetary systems is astronomical. We might be looking at a cosmic iceberg, with the tip being our familiar, baryonic universe, and the vast, invisible bulk being made of something else entirely. The consequences spiral outward from there. If there are non-baryonic planets, might there be non-baryonic moons, or belts, or rings? Could dark matter form complex systems with gravitational interactions similar to those of our own solar system? Could there even be dark matter stars, radiating only through gravitational waves, or perhaps forming binaries with baryonic stars? Every layer of possibility stretches the imagination further, but none of it breaks known physical laws. The laws of gravity do not care what kind of matter they govern. Detection remains the most formidable challenge. Since non-baryonic matter doesn't interact electromagnetically, it can't be observed through any traditional telescope. But researchers are exploring indirect methods. One involves looking for anomalies in the orbits of baryonic objects, like distant stars or galaxies, that suggest the presence of massive, invisible companions. Another approach involves gravitational microlensing, where the light from a background star is temporarily brightened and distorted by a massive object passing in front of it. If a dark planet were to pass between us and a star, the distortion could reveal its existence, even if the object itself emits no light. We may have already seen these events without realizing it. Some microlensing anomalies remain unexplained. Some orbital calculations don't quite add up. These loose threads may one day be tied together in a theory that confirms the existence of non-baryonic planets. And when that day comes, the floodgates of speculation will open even wider. Because if dark planets exist, then everything we assume about planet formation, cosmic evolution, and even the potential for life may need to be revised. It is tempting to imagine what such a planet might feel like up close. Not in the sensory sense, because, by definition, you could never see or touch it, but in terms of gravitational influence. You might float into a region of space that seems utterly empty, only to find your trajectory inexplicably altered. You might feel the tug of a massive body with no visible source. A non-baryonic planet could lurk in the space between stars, in the halo of the Milky Way, or even in the outer reaches of our own solar system, hidden beyond the Oort cloud, waiting to be discovered through a gravitational whisper. What if, beyond the Kuiper belt, there's a massive, unseen object bending the orbits of trans-Neptunian objects? Some scientists have proposed a Planet 9 to explain these orbital anomalies. What if Planet 9 isn't just a rogue gas giant, but something far stranger? What if it's a dark planet? Now imagine a universe where dark matter, under the right conditions, also collapses into clumps, not by electromagnetic interaction, but through gravity alone. It wouldn't form disks in the way baryonic matter does, but it might still cluster. Over time, those clusters could become dense enough to form planet-sized bodies. These bodies wouldn't sparkle. They wouldn't shine. They wouldn't radiate heat the way conventional planets do. But they'd have mass, and that mass would bend space itself. The biggest hurdle in conceptualizing non-baryonic planets lies in the fact that dark matter doesn't seem to clump on small scales, at least not according to our current simulations. Dark matter appears to form halos around galaxies, huge ghostly scaffolds that cradle the visible universe. But could there be smaller substructures hiding within these halos? Could localized overdensities of dark matter be gravitationally stable enough to form something planet-like? The answer, while uncertain, isn't a definitive no. And in the uncertainty lies possibility. If non-baryonic planets do exist, they would be completely invisible to traditional observation methods. They wouldn't block starlight in transits. They wouldn't emit infrared radiation. They wouldn't reflect starlight. Our only hope of finding them would be through their effects on other objects. Imagine a star with a peculiar wobble, one that doesn't correspond to any visible companion. Or a rogue exoplanet drifting through space that, inexplicably, is being influenced by something invisible nearby. These would be the breadcrumbs. There's also another tantalizing scenario: binary systems involving one visible and one non-baryonic body. If a non-baryonic planet orbited close to a neutron star or a white dwarf, we might detect strange anomalies in the timing of pulsar signals or unusual gravitational interactions. These anomalies, if not attributable to known objects, could hint at dark matter companions, non-baryonic planets silently orbiting in the shadows. What makes this even more compelling is the nature of dark matter itself. It's not just one substance. The term dark matter is really a placeholder for a wide category of hypothetical particles. It could be cold and slow-moving, or warm and fast. It could be composed of exotic particles like sterile neutrinos, or axions, tiny, elusive particles predicted by extensions of the Standard Model. And if different types of dark matter exist, then the possibilities for what kinds of structures they might form expand dramatically. A non-baryonic planet made of one kind of dark matter might behave very differently than one composed of another. One might be diffuse and ghostly, another dense and compact. One might pass through Earth without a trace, another might exert measurable gravitational force as it sweeps by. We might even be flying through the outer atmosphere of one right now and not even know it. And there's a haunting possibility to consider. What if non-baryonic planets are already orbiting in our own solar system? It would be like watching a pendulum swing with a subtle, unexplainable hesitation, a momentary pause that hints at an invisible hand tugging on the mechanism. Over time, as the data accumulates and the models refine, scientists might notice an anomaly, a planet-sized mass orbiting the pulsar, but completely invisible to all wavelengths of light. If confirmed, such a discovery would force us to confront the reality that planetary systems might not be exclusively baryonic. In fact, our own galaxy might already be teeming with such hidden worlds. The sheer implications of this idea stretch across cosmology, particle physics, and even philosophy. What if life could arise on such planets? Not life as we understand it, bound to carbon chains and liquid water, but a wholly different form, perhaps based on exotic interactions, existing in a realm far colder and quieter than any place we've studied? Of course, this enters speculative territory, but even as a hypothetical, it challenges the anthropocentric framework through which we interpret the cosmos. Non-baryonic planets wouldn't be restricted by the same thermal, chemical, or structural limits that define traditional planetary bodies. They might not have atmospheres in any meaningful sense. They wouldn't erode, rust, or burn. Their surfaces, if such a thing could be said to exist, would be dominated by gravitational balance, not geological activity. Without electromagnetic interactions, concepts like heat and cold, texture and color, become meaningless. Yet they could persist, ancient, silent, undetectable. Detecting them would require revolutionary methods. We may need gravitational interferometers of unimaginable sensitivity, capable of catching the faintest whisper of warping spacetime. or perhaps indirect detection through anomalies in cosmic microwave background radiation or the orbital mechanics of outer solar system objects. Even now, astronomers are puzzled by certain trans-Neptunian objects whose paths suggest the presence of a large unseen mass. While most speculate this to be a traditional Planet 9, there's a fringe possibility. It could be a non-baryonic mass casting a gravitational shadow from the dark. If such a planet did exist in our solar system, it would change the way we map space. Our celestial maps are built on light, reflected, refracted, and emitted. A dark planet would force us to consider maps based solely on mass and motion. Gravitational topography would become a new frontier in cartography, one where ghostly masses glide through space, altering trajectories, warping orbits, yet leaving no visible trace. It's an almost Lovecraftian concept, behemoths lurking just beyond the veil of perception, immune to light, timeless in presence. Scientific models would have to evolve. Currently, dark matter is modeled as a pressureless fluid, uniform and inert on small scales. But that assumption may be flawed. What if certain types of dark matter particles do clump, given the right conditions? Perhaps these clumps, seated in the early universe, survived as relics of formation. And perhaps some of them coalesced into forms indistinguishable in mass and shape from planets, yet utterly alien in substance. The idea gains further traction when considering self-interacting dark matter. Some theories propose that dark matter isn't completely inert. It may interact with itself via a hidden force, analogous to electromagnetism, but entirely separate from the standard model. If true, then non-baryonic matter could, under the right conditions, cool and collapse similarly to baryonic gas, albeit through unknown mechanisms. In such a model, dark planets become not just plausible, but statistically inevitable. This opens the door to dark solar systems, entire architectures of non-baryonic planets orbiting dark stars, themselves composed of dense clumps of dark matter. These systems would be invisible to us, slipping silently between galaxies, or perhaps hiding within them, camouflaged in gravity wells and motion curves. They might vastly outnumber traditional systems, with each visible star just a fraction of the total galactic content. If true, the visible universe is just the tip of an unseen, majestic iceberg. Consider also the possibility that baryonic and non-baryonic systems are not mutually exclusive. What if certain stars have both visible and invisible planets? The gravitational ballet of such systems would be incredibly complex, non-baryonic planets crossing the orbits of baryonic ones, creating unexplained anomalies in motion, perhaps even inducing orbital eccentricities or axial tilts that we currently write off as chaotic. Moreover, if non-baryonic matter is immune to electromagnetic interaction, then these planets would be impervious to radiation, storms, solar winds, and even supernova blasts. They could exist in places where baryonic planets would be vaporized, close to black holes, within the accretion disks of quasars, or floating serenely in galactic voids where light rarely travels. Their silence isn't just a factor of composition, it's a testament to their resilience. We must also reconsider what constitutes a planet. The official IU definition hinges on mass, orbit, and clearing the neighborhood, but it assumes detectability through light-based observation. A non-baryonic planet challenges that definition, pushing us toward a more inclusive model based solely on gravitational influence and spatial dynamics. In doing so, it forces us to confront a deeper truth. We define reality through what we can perceive. And non-baryonic planets stand as a direct rebuke to that arrogance. If we shift to computational astronomy, the potential for discovery widens. Simulations of dark matter distributions in the early universe reveal filamentary structures, cosmic webs stretching across billions of light years. Within these webs, nodes of high density emerge. These nodes could contain regions where dark matter, through gravity or self-interaction, formed compact objects. Some might be stars, some brown dwarf-like structures, and some might be planets. Artificial intelligence, trained on vast troves of astrophysical data, could begin to identify anomalies suggestive of non-baryonic bodies. Machine learning models could detect patterns invisible to the human eye, subtle wobbles, statistical outliers, unexpected gravitational microlensing events. These signals, when compiled, might reveal a hidden population of objects with no spectral signature, but definite mass. Microlensing may be our most powerful tool in this hunt. When a massive object passes in front of a distant star, it can bend and amplify the star's light, if only briefly. This gravitational lensing doesn't depend on the object's composition, only its mass. Several microlensing events have already been observed that defy categorization. Could some of them have been caused by non-baryonic planets? We can't say for certain yet, but the method holds promise. In 2016, a team using the Subaru telescope discovered a population of free-floating planetary mass objects in the Milky Way, rogue planets not tethered to any star. These planets could be the tip of the iceberg. Some may not be planets at all in the conventional sense, but rather a blend of baryonic cores surrounded by dark matter envelopes, or entirely non-baryonic in composition. This introduces the notion of hybrid worlds, strange chimeras where dark and light matter coexist in gravitational symbiosis. If hybrid worlds exist, they might be detectable through subtle deviations in density or thermal output. A planet composed mostly of dark matter would not radiate heat as expected. It might be denser than it appears, or conversely, lighter than its gravitational effects suggest. Discrepancies in mass-radius relationships for certain exoplanets have already been noted. While most are explained through atmospheric composition or core structure, a few remain puzzling. The mind reels at the philosophical consequences. For centuries, humanity has looked to the stars and seen reflections of itself, familiar forms, albeit strange and distant. Non-baryonic planets force us to look into a mirror that returns no image. They strip away our assumptions and invite us to contemplate a universe where invisibility is not a trick, but a fundamental state of being. These planets, if they exist, don't just alter astronomy, they challenge the limits of human perception. The discovery of a non-baryonic planet near the outskirts of our solar system would force a reevaluation of current astronomical models. Traditionally, we have understood planetary formation through the lens of baryonic matter, atoms, dust, and gas clouds that condense under gravity to form solid bodies. However, a non-baryonic planet, by nature of being composed of dark matter or some other exotic form of matter, could have completely different formation processes. It might not need to undergo the same violent accretion processes that a traditional planet experiences. Instead, it could form through gravitational clustering of dark matter particles or interactions between dark matter and a hidden force not yet understood. The first challenge in confirming such a planet would be the detection method itself. We are accustomed to detecting planets through their interaction with light, either through reflected light, emitted heat, or gravitational microlensing. A non-baryonic planet, impervious to electromagnetic radiation, would refuse to reveal itself in the same ways. Therefore, we would need to rely on indirect detection methods, such as gravitational perturbations or subtle shifts in the paths of nearby objects. Advanced gravitational wave detectors or more refined space telescopes might eventually offer the means to detect such a planet, but it would require patience, innovation, and time. The implications of finding such an object extend far beyond just revising our models of planetary formation. It would prompt a reevaluation of dark matter itself. Currently, we understand dark matter as an invisible substance that only interacts through gravity and possibly a weak nuclear force. However, if non-baryonic planets exist, it suggests that dark matter may be more complex than we thought. It might have a form that can accumulate, clump together, and create bodies that exert gravitational influences just like baryonic planets. These planets would be proof of the clumpy nature of dark matter, validating some of the more speculative models of dark matter interactions and casting new light on the universe's most elusive substance. This revelation could even have philosophical implications. For centuries, humanity has envisioned the universe through the lens of matter that we can see, touch, and measure. A non-baryonic planet challenges this paradigm, forcing us to reconsider the limits of human perception. It could also redefine what it means to be a planet. We typically associate planets with the ability to support life, whether microbial or more advanced. But what if life could arise on a non-baryonic planet, where the building blocks of carbon-based biology don't apply? Would life, as we understand it, be the only way to define it? Or would these planets harbor forms of existence that are entirely foreign to our current comprehension? Moreover, the discovery of a non-baryonic planet would fuel deeper questions about the structure and evolution of the universe. Could there be entire regions of the universe populated by invisible, non-baryonic worlds, existing in a delicate balance with visible stars and galaxies? Perhaps these dark systems are as numerous, if not more so, than the ordinary ones we observe. We might even begin to realize that the vast majority of mass in the universe resides not in visible galaxies and stars, but in these dark and mysterious structures. The challenge of studying such planets would extend beyond just detection. If a non-baryonic planet were discovered, scientists would need to develop entirely new methods of studying and characterizing it. For instance, scientists rely heavily on spectroscopic data to understand the atmospheres of planets, identifying chemical compounds, gases, and weather patterns. With non-baryonic planets, such methods would be impossible due to their lack of interaction with light. New instruments, sensitive to gravitational waves or other exotic interactions, would need to be developed to investigate the properties of these planets in any meaningful way. The discovery would also raise questions about the formation and evolution of galaxies themselves. Non-baryonic planets would likely form in environments where regular matter cannot easily coalesce, leading us to rethink how galaxies evolve. Dark matter, which is believed to make up a large portion of a galaxy's mass, might play a more active role in galactic dynamics than we currently realize. Non-baryonic planets might form in the halos of galaxies, where dark matter is most abundant, or they could exist in the vast empty regions between galaxies, entirely disconnected from any visible star or planet. These rogue, invisible worlds could represent a new frontier in understanding the gravitational interactions that govern the cosmos. And yet, the implications go beyond just scientific curiosity. Discovering non-baryonic planets might force humanity to reconsider its place in the universe. The discovery of an invisible planet would be a reminder that our knowledge of the cosmos is still in its infancy. The universe is vast and full of mysteries we have yet to uncover, and each discovery like this pushes the boundary of human understanding further. It might also inspire future generations to explore the unseen, to develop new technologies, and to pursue questions that we have only begun to scratch the surface of. Such a discovery could also have an impact on how we think about space exploration. Traditional missions have been based on the assumption that planets are made of baryonic matter, and that they can be explored through methods that detect electromagnetic radiation. But what if the planets we seek to explore aren't visible in the traditional sense? What if we need to develop entirely new methods for exploring these hidden worlds? Would we have to rethink how we search for habitable zones or potential extraterrestrial life? The technology that could uncover non-baryonic planets might also open the door to more advanced space exploration techniques, enabling us to peer deeper into the universe than ever before. The hypothetical existence of non-baryonic planets presents a tantalizing and unsettling mystery. It challenges the very foundations of our understanding of the cosmos, and hints at a universe far stranger than we ever imagined. Whether or not these planets exist is still an open question, but the possibility is enough to remind us of how little we truly know about the universe that surrounds us. If non-baryonic planets do exist, they would not only reshape our view of planets and dark matter, but they would also provide a glimpse into the unseen forces that govern the universe. The discovery of these hidden worlds could lead to a revolution in astrophysics, philosophy, and even our understanding of the nature of life itself. We would be forced to expand our definitions of what is possible, challenging everything we thought we knew about the nature of existence. Only time, innovation, and perseverance will reveal whether these dark, elusive worlds are real, and if so, what mysteries they hold. As we continue to explore the theoretical nature of non-baryonic planets, the tantalizing implications of their existence begin to raise questions not only about planetary formation but also about the fundamental forces of the universe. The discovery of such a planet would demand a profound shift in how we approach the physics of the cosmos. One of the most immediate questions would be about the interaction of non-baryonic planets with the fabric of spacetime itself. Currently, we understand that mass, whether from visible or invisible sources, can bend spacetime, as demonstrated by Einstein's theory of general relativity. However, dark matter, which comprises the bulk of a non-baryonic planet, behaves differently from ordinary matter. While dark matter interacts gravitationally with visible matter, it doesn't interact with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light. In theory, a non-baryonic planet could have a profound gravitational effect on its surroundings, warping spacetime in ways that we are just beginning to understand. Imagine if a non-baryonic planet passed through a region of space already occupied by ordinary baryonic matter, perhaps a distant star system. The gravitational forces of this non-baryonic planet could potentially warp the light from the star, causing what astronomers call gravitational lensing. While gravitational lensing has already been observed in cases of massive objects like galaxies, a non-baryonic planet might exhibit a different kind of lensing effect, perhaps due to the unique properties of dark matter. This could provide one of the first observational clues to the planet's existence, by detecting the distortion of light as it travels past the non-baryonic mass. Moreover, the motion of such a planet through the cosmos could reveal important details about the distribution of dark matter in the universe. Dark matter, as we know, doesn't just sit still. It is spread throughout the universe in a cosmic web-like structure, and its influence on the formation and evolution of galaxies is undeniable. If non-baryonic planets exist, they could serve as tracers of dark matter, providing us with a new way to map the invisible structures that make up much of the universe's mass. By tracking their movements, we might uncover the underlying structure of dark matter itself, and in turn, refine our understanding of the larger cosmological landscape. This search for dark matter's secrets could also be a pathway to discovering other exotic phenomena that were once thought to be purely theoretical. For example, some scientists have suggested that certain forms of dark matter might possess the ability to clump together and form dark stars, which could emit dark radiation or interact in ways that are entirely alien to our current understanding. A non-baryonic planet could be the first hint that dark matter is more than just an abstract idea. It could be the key to unlocking entirely new types of cosmic objects. If such planets are indeed composed of dark matter, their gravitational properties could potentially challenge or confirm several ongoing hypotheses about the behavior of dark matter on a smaller scale. Could it be that dark matter forms more complex structures, potentially even mimicking the formation of ordinary planets, but through completely different means? Or is it possible that dark matter, which interacts weakly with regular matter, is far more elusive, existing in more ephemeral forms that we have yet to detect? What would it mean for astrophysics and our understanding of physics if non-baryonic planets, and their corresponding dark matter signatures, turn out to be the norm rather than the exception? For one, we would have to radically rethink how we understand gravitational theory. Currently, we model gravitational interactions based on the assumption that mass is composed of baryonic particles. If non-baryonic planets are common, we would need a new framework that accounts for interactions between dark and visible matter. This could potentially lead to a major shift in our understanding of gravity, suggesting that the force behaves differently at larger or more distant scales, particularly when dark matter is involved. But the implications of discovering non-baryonic planets extend beyond the realm of physics. For centuries, humanity has been captivated by the possibility of life beyond our own world. We have speculated about the potential for life on other planets, imagining worlds filled with water, air, and the building blocks of life as we know it. But what if life could exist in forms completely foreign to us? Could a non-baryonic planet be home to life that doesn't require the same physical laws that govern our own biology? If life can emerge under conditions that are completely different from what we experience, it might open up the possibility of discovering life forms that are not only radically different from what we know, but also beyond our ability to detect with current technology. This thought experiment challenges our very definition of life. On Earth, life is carbon-based and depends on chemical reactions, energy transfer, and complex molecular structures. But if a non-baryonic planet exists, what could life look like if it were based on dark matter or some other exotic form of matter? Could life exist without interacting with light? Could it thrive in the absence of physical, chemical, or biological processes we recognize? These questions delve into the speculative, but they also serve as a reminder of just how much we have yet to understand about the cosmos and its potential for harboring life in ways we haven't even imagined. Furthermore, the discovery of non-baryonic planets could reshape our understanding of the origin and fate of the universe. We know that the universe began in a hot, dense state during the Big Bang and has since expanded. However, the specific details of how structures like galaxies, stars, and planets formed remain a mystery. Could non-baryonic planets have played a role in this process? If they are common in the universe, their influence on cosmic evolution could be profound. Perhaps dark matter itself played a crucial role in the formation of galaxies, helping to stabilize the structures we observe today. Understanding how non-baryonic planets fit into this larger picture could reveal new insights into the formation of the universe itself, shedding light on processes that took place long before the first stars began to shine. The search for non-baryonic planets would push the limits of current technology and inspire the development of new tools to explore the universe. As our telescopes become more powerful and our ability to detect subtle gravitational effects improves, we may be on the verge of a new era of discovery. The quest to find these invisible worlds would drive innovation in fields ranging from physics to engineering, and the technologies developed along the way could have far-reaching applications in other areas of science and even everyday life. The hypothetical existence of non-baryonic planets represents one of the most exciting frontiers in modern astrophysics. These planets would not only challenge our current understanding of planetary formation and dark matter, but they would also force us to reconsider what it means to be a planet, and perhaps even to rethink our definition of life itself. Whether or not non-baryonic planets exist, their potential discovery would ignite a scientific revolution, inspiring future generations of astronomers, physicists, and thinkers to look beyond the visible and explore the mysteries of the invisible universe that surrounds us. The idea of non-baryonic planets also draws attention to the evolving relationship between visible and invisible matter in the universe. For decades, scientists have sought to understand how these two types of matter interact. Baryonic matter, the ordinary matter that makes up stars, planets, and everything we can see, is only a small fraction of the universe's total mass. The rest is believed to be made up of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it undetectable by conventional means. As such, dark matter has remained elusive, detectable only by its gravitational influence on galaxies, galaxy clusters, and large-scale structures in the universe. However, as we imagine the possibility of non-baryonic planets, we are forced to confront some uncomfortable truths about our limitations as human observers. We rely heavily on electromagnetic radiation, light, radio waves, X-rays, to study distant objects in the universe. But non-baryonic planets, composed primarily of dark matter, would be nearly invisible to our current technology, offering a profound challenge to astronomers. The methods used to detect exoplanets, like the transit method, measuring the dip in light as a planet passes in front of its star, or radial velocity, measuring the star's wobble as it responds to the gravitational pull of an orbiting planet, would be ineffective in the case of non-baryonic planets. These planets would not reflect or block light in a way that would make them detectable through these methods. The absence of detectable electromagnetic radiation would make their discovery incredibly difficult. So, how could we detect a non-baryonic planet? As already mentioned, gravitational lensing could potentially offer one of the best clues, where the planet's mass bends and distorts the light from a background star. This effect could be used to map out the planet's location and mass, providing indirect evidence of its existence. Similarly, the gravitational influence of a non-baryonic planet could cause detectable changes in the orbits of nearby objects, such as a star or a gas giant. This, too, would give astronomers a way to infer the presence of a planet without seeing it directly. But while gravitational signatures might point us in the right direction, much more sophisticated techniques would likely be needed to truly understand these hypothetical worlds. New instruments capable of detecting subtle variations in gravitational fields, along with powerful computational models to simulate the complex interactions between dark matter and ordinary matter, would be essential in the search for non-baryonic planets. In essence, these planets would demand that we build entirely new methods of detection, much in the same way that the discovery of exoplanets itself has revolutionized astronomy in the last few decades. The more we think about it, the more we realize that a non-baryonic planet might not just be a strange curiosity but could hold the key to answering some of the deepest questions in physics. What if these planets could serve as a bridge between the dark and visible sides of the universe? Dark matter, after all, is one of the greatest unsolved mysteries of modern physics. It's believed to account for a significant portion of the universe's mass, but we have no direct way of detecting it. If non-baryonic planets were made of dark matter, they could offer the rarest of opportunities, a direct, albeit indirect, link to understanding how dark matter behaves on a macroscopic scale. The discovery of a non-baryonic planet might also force us to reconsider some of the very foundations of cosmology. For instance, current models of the formation of planets are based on the assumption that they are made up of baryonic matter, formed through the accretion of dust and gas. But what if this process works differently for non-baryonic planets? Could they form in ways that are completely independent of the processes that govern baryonic matter? Could dark matter self-organize into planetary-like structures, influenced not by nuclear fusion or chemical bonds, but by entirely different forces? Some theories suggest that dark matter might have unique properties that could allow for its aggregation into dense objects, not unlike how normal matter condenses to form planets. In fact, there's speculation that the interaction between dark matter and ordinary matter could lead to the creation of dark matter hubs, where large amounts of dark matter clump together, much like how gas clouds collapse to form stars. If these clumps of dark matter were able to collapse into a planetary structure, they could potentially exhibit gravitational behavior similar to that of ordinary planets. This theory could fundamentally change how we think about the composition of the universe, adding another layer of complexity to our models of planetary formation and evolution. It's also worth considering the impact that non-baryonic planets might have on our understanding of the large-scale structure of the universe. Dark matter plays a critical role in the formation of galaxies and galaxy clusters. It's believed that the gravitational effects of dark matter have helped shape the galaxies we observe today. If non-baryonic planets were common, they could offer additional insight into how galaxies formed in the first place. Could these planets have existed in the early universe, influencing the development of galaxies and possibly even the conditions necessary for the emergence of stars and life? Moreover, the existence of such planets could offer a unique glimpse into the future of the universe. Dark matter is thought to be a key player in the universe's expansion. Some cosmologists have speculated that the presence of dark matter could be responsible for the accelerated expansion of the universe, as observed through the redshift of distant galaxies. Non-baryonic planets could potentially provide further clues as to how dark matter will shape the universe's evolution over time. As the universe continues to expand, and as more dark matter clumps together, could non-baryonic planets become more common? Or could they eventually play a role in the eventual fate of the cosmos? Ultimately, the discovery of a non-baryonic planet would not just be an exciting chapter in the search for exoplanets. It would be a milestone in the ongoing effort to understand the very fabric of the universe. By unraveling the mysteries of dark matter, we could unlock answers to some of the most profound questions in science. What is the true nature of the universe's mass? How do the forces of gravity and electromagnetism interact on a cosmic scale? And perhaps most intriguingly, are there forms of life beyond our comprehension, existing on worlds made of substances that we are only beginning to understand? All of these questions hinge on the possibility of non-baryonic planets, and while they remain hypothetical, the prospect of their discovery is enough to spark a renewed sense of wonder and curiosity about the universe we inhabit. As our technologies improve and our understanding of dark matter deepens, we may one day find ourselves standing on the threshold of a new era in astronomy, one in which invisible worlds, hidden from our senses, reveal their secrets in ways that could reshape our understanding of the cosmos forever. The continued exploration of non-baryonic planets brings with it not only a wealth of scientific inquiry but also philosophical considerations about the nature of the universe and humanity's place within it. Imagine a world, or rather a planet, that is not composed of the atoms and particles that we are familiar with. A planet formed from the elusive dark matter, existing in a realm where the conventional laws of physics might bend or behave differently. If such planets existed, they could challenge the very definitions of what it means to be a planet. Our current understanding of planetary formation, structure, and behavior might not apply at all. This scenario invites a deeper questioning of the limitations of human knowledge and the vastness of cosmic possibilities. Non-baryonic planets, if they exist, would be fundamentally different from those we know. Our current methods for studying planets, such as looking at the way light reflects off their surfaces, analyzing their atmospheres, or measuring their temperatures, would be practically useless in the case of non-baryonic planets. These planets would likely not have a visible surface to reflect light, and without the typical atomic interactions that generate heat signatures or emissions, detecting them would require completely new methods of exploration. This would push the boundaries of astrophysics and force scientists to reconsider what we even consider observable or detectable in the universe. Given that dark matter itself is invisible and interacts weakly with electromagnetic radiation, a non-baryonic planet might be a perfect candidate for advancing a new theory of astrophysical observation. One avenue of exploration would involve gravitational interactions. As previously discussed, these planets would likely have a gravitational effect on nearby stars or other cosmic objects, even though they do not emit light. This means that while we may not be able to see the planet, we could potentially measure its presence by observing how nearby objects behave. However, there's an even deeper mystery here. The very nature of dark matter itself is still largely unknown. While we know it has mass and exerts gravitational pull, we do not yet understand what dark matter is made of. Theories abound, with some scientists proposing that it could be composed of weakly interacting massive particles, WIMPs, axions, or sterile neutrinos, none of which have been directly detected so far. The mere existence of non-baryonic planets could shed light on the true nature of dark matter. If such a planet were discovered, it could provide evidence of the properties of dark matter in a way that no other method has been able to. For example, it could help confirm or rule out certain theories about dark matter particles and how they interact with regular matter. This line of inquiry opens the door to some extraordinary possibilities. What if non-baryonic planets could give us a glimpse into the conditions that existed in the very early universe? When the universe was only a few minutes old, it was a hot, dense soup of elementary particles. As it expanded and cooled, matter began to form into the galaxies, stars, and planets we see today. But dark matter, unlike ordinary matter, has never been detected directly. Its interaction with the universe's first moments remains shrouded in mystery. A non-baryonic planet might provide us with a snapshot of this mysterious phase of cosmic evolution, offering clues that could inform our understanding of the Big Bang, the formation of galaxies, and the ultimate fate of the universe. The search for non-baryonic planets also invites us to rethink what we might consider life-friendly planets. While the classic search for extraterrestrial life has focused on finding planets with liquid water, an atmosphere, and the right chemical ingredients, non-baryonic planets could present a radically different set of criteria for habitability. Imagine life existing in a world where normal matter does not dominate, and the very fabric of existence is influenced by dark matter. How would life adapt in such an environment? Could there be forms of life that thrive in the absence of visible matter, living in a dark, invisible universe that we could barely comprehend? The possibility of life on non-baryonic planets could open up an entirely new realm of astrobiology, one where life might not be carbon-based or rely on water in any form. Perhaps these hypothetical forms of life would be fundamentally different from anything we can imagine, based on principles of physics and chemistry that are outside of our current understanding. This prospect challenges our very conception of life and what it takes to support it. Could life exist in a dimension where dark matter rules, perhaps taking forms we would not recognize? It's not as far-fetched as it seems. As we learn more about the complexities of biology and the diversity of life on Earth, it becomes increasingly apparent that life is much more adaptable than we once thought. Non-baryonic planets could provide the most extreme test case for life's potential to survive in entirely different conditions. The implications of such a discovery would reverberate through every field of science, from cosmology and physics to biology and philosophy. It would force humanity to expand its thinking beyond the confines of ordinary matter, potentially unlocking the secrets of the universe that have eluded us for centuries. Could the discovery of a non-baryonic planet eventually lead to a breakthrough in our understanding of dark matter and its relationship with regular matter? Could it help answer questions about the fundamental forces that govern the universe, such as gravity, electromagnetism, and the weak and strong nuclear forces? If non-baryonic planets were to exist, they would provide a unique laboratory for testing these ideas and more. One of the most profound questions that might arise from the discovery of non-baryonic planets is the role of dark matter in the larger cosmological picture. Dark matter is not just an anomaly, it is a crucial component of the universe's mass-energy budget. The existence of non-baryonic planets could force us to rethink how we model the large-scale structure of the universe. If dark matter plays such a critical role in planetary formation, perhaps we have been overlooking an entire category of celestial bodies, one that could be much more common than we initially thought. The discovery of non-baryonic planets could change our models of galaxy formation, stellar evolution, and even the future of the universe. But there are also philosophical implications of such a discovery. Non-baryonic planets would be invisible to us, not because they are too far away, but because they do not interact with light in the ways that we expect. If we could confirm the existence of such planets, it might lead us to question the limits of human perception. What else could be out there, hiding just beyond the reach of our senses? What else exists in the universe that we cannot detect using our current methods of observation? The possibility of invisible, non-baryonic worlds reminds us that there may be more to reality than meets the eye. In many ways, the discovery of non-baryonic planets would be the beginning of a new era in astrophysics. It would signal that our universe is far more complex and mysterious than we ever imagined. It would raise new questions, present new challenges, and force us to rethink our most fundamental assumptions about the cosmos. What lies ahead in the search for non-baryonic planets? It is impossible to say, but one thing is certain: the pursuit of this knowledge will continue to push the boundaries of human understanding, driving us to explore deeper into the unknown reaches of the universe. As we push forward in the exploration of non-baryonic planets, the importance of theoretical models cannot be overstated. In the absence of direct observations, much of the research on these hypothetical planets relies on simulations, advanced physics models, and indirect evidence. To even begin understanding how such a planet might behave, scientists must delve into realms of theory that stretch the very limits of our understanding of particle physics, gravity, and cosmology. These models must incorporate dark matter's role in the universe, how it interacts with baryonic matter, and what physical laws govern a world composed of materials we cannot see. One crucial aspect of this theoretical investigation is the study of gravitational anomalies. Planets made of non-baryonic matter, assuming they are composed of dark matter or another exotic substance, might exhibit gravitational effects that are distinct from those of ordinary planets. These effects could be seen in their gravitational pull on surrounding objects, like moons or other celestial bodies, or even in how they interact with light and other forms of electromagnetic radiation. If we could detect such anomalies, even without seeing the planet itself, it would represent a breakthrough in our ability to study invisible matter. Scientists might use these gravitational anomalies as a basis for new techniques to detect non-baryonic planets. For example, they could employ gravitational lensing, an effect where the gravitational field of a massive object bends the light of objects behind it, to look for distortions that could indicate the presence of a planet. Another possibility is to observe the motion of stars within a galaxy to detect subtle changes in their trajectory caused by the gravitational influence of a non-baryonic planet. This would be a difficult task, but the potential rewards are immense. Beyond gravitational effects, the study of non-baryonic planets would also require new technologies and observational tools. Currently, we are limited by the instruments available for observing the cosmos. Telescopes that rely on detecting visible light, infrared radiation, or radio waves are insufficient for detecting dark matter directly, as it does not interact with these types of radiation in the usual way. What would be required is a new generation of instruments that can probe the universe on a fundamentally different level, one capable of detecting the presence of dark matter through its unique interactions with gravity or other yet-to-be-identified forces. These instruments would need to operate in ways that allow them to gather information from the cosmic depths where ordinary matter and dark matter exist side by side. One intriguing possibility lies in the study of how non-baryonic planets might interact with the cosmic microwave background (CMB) radiation, the faint glow that permeates the universe and is a remnant of the Big Bang. The CMB is one of the few pieces of evidence we have for understanding the early universe, and any disturbance or shift in this background radiation caused by dark matter planets could provide valuable clues. While the CMB is typically used to study the distribution of regular matter in the universe, non-baryonic planets could leave their mark in subtle but detectable ways, giving us yet another tool for discovering their existence. If non-baryonic planets were confirmed, they would also add to our understanding of the composition and distribution of dark matter in the universe. Currently, dark matter is thought to make up approximately 27% of the universe's mass energy content, yet we have only indirect evidence of its existence. Its elusive nature has made it one of the most profound mysteries in modern science. The discovery of non-baryonic planets could help fill in the gaps in our understanding of dark matter's role in the formation and evolution of the universe. What is its true nature? How does it interact with regular matter, and could it play a part in the formation of stars, galaxies, and even life itself? These are the kinds of questions that would be addressed by the discovery of non-baryonic planets. In this light, these planets could serve as a natural laboratory for testing new theories in particle physics, cosmology, and astrophysics. For instance, they could help scientists refine models of the early universe, such as the way galaxies first formed. Understanding how dark matter behaves in planetary environments could provide insights into how it has shaped the larger structures we see today. The way in which non-baryonic planets interact with their surroundings could give us clues about the conditions that allowed galaxies to coalesce and stars to form. It might even shed light on the elusive dark energy that is believed to be accelerating the expansion of the universe. Moreover, the discovery of non-baryonic planets could have far-reaching implications for the search for extraterrestrial life. As we broaden our search for life beyond Earth, we have traditionally focused on planets with liquid water, a stable atmosphere, and the right chemical elements for life as we know it. However, the discovery of non-baryonic planets would force us to expand our definition of what constitutes a habitable world. Could life exist in such a radically different environment, one where ordinary matter is not the dominant force? It's a question that raises more philosophical than scientific debates, but it is one that could shape future research in astrobiology. Perhaps life could arise in forms we cannot even begin to conceptualize. Astrobiologists have long speculated about the potential for life to exist in extreme environments, such as the deep oceans of Earth, where life thrives in the absence of sunlight. If non-baryonic planets exist, they would present an entirely new set of environments to consider. Perhaps these planets are home to life forms that have evolved under completely different conditions, potentially based on principles of physics and chemistry that are entirely foreign to us. These life forms could possess abilities and traits that would defy our current understanding of biology, presenting new challenges and opportunities for scientific inquiry. In addition to the scientific and philosophical challenges, the discovery of non-baryonic planets would also have profound implications for our understanding of the universe's future. If these planets are common in the universe, it could suggest that dark matter is not a mere anomaly, but a fundamental component of cosmic evolution. If non-baryonic planets form in the same way that regular planets do, it might suggest that the future of the universe could be shaped by dark matter in ways we have yet to fully grasp. This could lead to new theories about the ultimate fate of the cosmos, whether the universe will continue to expand indefinitely, collapse in a big crunch, or even evolve into something entirely unrecognizable. This uncertainty about the universe's future, combined with the potential to learn more about the very building blocks of reality, makes the discovery of non-baryonic planets one of the most exciting frontiers in modern science. It is a subject that encompasses not just physics, astronomy, and biology, but also challenges our very perception of what is possible in the cosmos. The search for these planets will continue to push the limits of technology, imagination, and human curiosity. The universe, after all, is far more complex than we can currently comprehend, and the discovery of non-baryonic planets may be just the beginning of an entirely new era in our exploration of the cosmos. The hunt for non-baryonic planets also brings with it a cascade of practical challenges. First and foremost, there's the issue of detection. As mentioned earlier, conventional tools like optical telescopes and even more advanced instruments that detect infrared or radio waves are not suited for detecting non-baryonic matter. This presents a significant hurdle, one that requires both new theories and new technologies. What if, in our search for these planets, we're overlooking the very signals that might offer their existence? There could be dark matter signatures or gravitational effects happening right under our noses, but because our instruments are designed for visible light or electromagnetic radiation, we might not even know how to recognize these signs. Researchers are actively developing specialized detectors that are capable of picking up signals that might indicate the presence of dark matter. One such approach involves using extremely sensitive instruments, such as cryogenic detectors, that are designed to capture the faintest of energy pulses. These devices could potentially detect the very rare interactions between dark matter particles and normal matter. Though the technology is still in its infancy, it holds promise for the future of non-baryonic planet detection. In addition to this, scientists are exploring more unconventional methods, such as using neutrino detectors to study the interactions between dark matter and other subatomic particles. If successful, these methods could revolutionize our understanding of non-baryonic planets. In parallel, astronomers are investigating whether they can detect the effects of non-baryonic planets indirectly. For instance, if such planets have a strong gravitational field, they may cause tiny, but measurable, disruptions in the movement of nearby stars or objects. By analyzing these gravitational interactions, it might be possible to infer the presence of a planet composed of dark matter, even if it cannot be seen directly. Moreover, these planets might exert influence on their surrounding environment in ways that regular, baryonic planets cannot, such as by distorting the trajectories of comets or other small celestial bodies passing through their system. Another approach that has been suggested involves studying the cosmic web, the vast network of dark matter that stretches across the universe. This dark matter is thought to form a sort of scaffold upon which galaxies, stars, and planets are built. If non-baryonic planets exist, they could potentially be embedded within these cosmic structures, their presence detectable through the gravitational lensing of light, or even distortions in the fabric of space-time itself. This would require incredibly precise measurements, perhaps even beyond what is currently possible with our best instruments. But the possibility is there, and this could be the next frontier in the search for non-baryonic matter. What makes this even more intriguing is the potential for non-baryonic planets to have fundamentally different chemical compositions than those composed of normal matter. In our current understanding, planets are formed when dust and gas coalesce due to gravity. These materials, largely composed of protons, neutrons, and electrons, give rise to the various forms of matter we are familiar with. But what if non-baryonic planets form under entirely different principles? If dark matter or another exotic substance is involved, the processes by which these planets are formed could be unlike anything we currently understand. They might emerge from the very fabric of spacetime itself, born not from dust clouds, but from an entirely different mechanism that we have yet to detect, or even imagine. This opens up a wealth of possibilities for what these planets might be like. Instead of having a solid surface or even a gaseous atmosphere like conventional planets, non-baryonic planets could be more like massive clouds of dark matter, loosely bound together by gravity. Alternatively, they might have a completely different form of matter, one that does not require the conventional atomic structure to maintain its shape. They could behave more like a fluid or even a field that changes its properties depending on external forces, such as nearby stars or the movement of other celestial objects. Understanding how these planets might behave requires pushing the limits of our imagination, as they would challenge everything we know about planetary science. The discovery of such a planet would also have profound implications for our understanding of the universe's composition. Currently, most of the universe is made up of dark matter and dark energy, with baryonic matter representing only a small fraction of the total mass energy content. However, as of now, dark matter has remained invisible to us, detected only through its gravitational effects on visible matter. The discovery of a non-baryonic planet could provide the first direct evidence of this invisible substance. If these planets are composed entirely of dark matter, it could open the door to understanding how dark matter behaves on a local scale, rather than just its large-scale gravitational effects on galaxies and clusters of galaxies. The concept of non-baryonic planets could even lead to a revolution in our understanding of the fundamental forces of nature. The current model of physics, the Standard Model, is based on the idea that all matter is made up of fundamental particles like quarks and leptons, which interact via the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But dark matter does not interact with the electromagnetic force in the same way that regular matter does, which is why it remains invisible to us. This suggests that there might be additional, as yet undiscovered, forces at play. If non-baryonic planets exist, they could provide us with a new window into these forces, leading to groundbreaking discoveries in particle physics and cosmology. As we continue to study these potential worlds, the quest for non-baryonic planets may take on an even more philosophical dimension. If planets made of dark matter, or other exotic substances, are possible, it raises the question of whether the universe is filled with other forms of matter that we have yet to detect. Could there be entire civilizations out there, hidden from our view, built from materials we cannot even conceptualize? These questions touch on some of the most profound mysteries of existence, ones that could redefine our place in the universe. Moreover, the implications of finding such planets extend far beyond the realm of science and into the realm of imagination. For millennia, humanity has looked up to the stars, wondering whether we are alone in the universe, whether other life forms exist, and what the future holds for the cosmos. The discovery of non-baryonic planets would not only answer many of these questions, but also create an entirely new set of questions. It would challenge our understanding of life, the formation of planets, and the very nature of the universe itself. In a world where the boundaries of knowledge are constantly being pushed, the search for non-baryonic planets could prove to be one of the most exciting and rewarding ventures in modern science. Whether or not these planets are ever found, the effort to discover them will undoubtedly lead to new insights and discoveries that will deepen our understanding of the cosmos and our place within it. It's a journey that may seem improbable now, but in the boundless expanses of the universe, anything is possible. The search continues. As we push forward into this uncharted territory, the question arises: what kind of technology will we need to truly understand and explore non-baryonic planets? At the moment, most of our instruments are optimized for detecting baryonic matter, or what we know as ordinary matter. Our telescopes and spacecraft are finely tuned to capture light, radiation, and gravitational waves from known objects such as stars, galaxies, and planets made up of ordinary matter. These are the signals that we're familiar with, signals that we can study, quantify, and model. However, non-baryonic planets, being composed of dark matter or other exotic forms of matter, don't emit light in the traditional sense. They don't radiate energy in the same way that conventional objects do, nor do they interact with electromagnetic radiation as normal matter does. This makes them incredibly difficult to detect. Thus, detecting non-baryonic planets would likely require a fundamental shift in how we approach space observation. One of the most promising technologies for detecting these planets may lie in the realm of gravitational waves. These waves, predicted by Einstein's theory of general relativity, are ripples in the fabric of space-time caused by massive objects, such as black holes or neutron stars, moving through space. They travel at the speed of light, and can carry information about the objects that created them. Gravitational wave detectors, such as LIGO and Virgo, have already opened up a new way of observing the universe, enabling us to study phenomena that were once invisible to traditional telescopes. What if gravitational waves could also provide clues to the existence of non-baryonic planets? If such planets exist, they might warp spacetime in subtle ways, creating gravitational waves that could be detected by our instruments. These waves would be extremely faint, likely requiring highly sensitive equipment to pick up. But the idea that we could hear these planets through the distortion they cause in spacetime is an exciting one. In fact, some theorists believe that the study of gravitational waves might be the key to unlocking the mysteries of dark matter, and by extension, the hidden worlds of non-baryonic planets. Another potential technology for detecting non-baryonic planets could involve the use of neutrino telescopes. Neutrinos are incredibly small, elusive particles that are produced in massive quantities by the Sun and other celestial bodies. While neutrinos interact very weakly with matter, they could still hold the key to understanding dark matter and non-baryonic planets. Neutrino detectors, such as the IceCube Neutrino Observatory in Antarctica, could potentially detect the interactions between dark matter particles and normal matter in the vicinity of these planets. Just as gravitational wave detectors have expanded our understanding of the universe, neutrino telescopes could help us detect signs of exotic, invisible matter. In addition to these high-tech approaches, there may be more theoretical work to be done in understanding the fundamental properties of non-baryonic planets. One of the big challenges in physics is that dark matter, which makes up about 27% of the universe's total mass energy, remains largely undetectable. We know it exists because of its gravitational effects on galaxies, galaxy clusters, and the cosmic microwave background radiation, but we don't know much about what it is made of or how it behaves. Some scientists suggest that dark matter could be made up of WIMPs, weakly interacting massive particles, axions, or other exotic particles. These particles would have mass and interact through gravity, but not through the electromagnetic force, which is why they don't emit light or other radiation. If non-baryonic planets are composed of dark matter, their properties would likely be determined by the specific particles that make them up. For instance, if these planets are made of WIMPs, they might have a strong gravitational pull but no observable light emissions. The exact structure and behavior of a planet composed of such exotic particles are currently beyond our understanding but could be one of the most exciting frontiers in modern physics. Exploring the interior of a non-baryonic planet would also pose significant challenges. Traditional planetary science relies on understanding the composition of a planet by analyzing its surface and atmosphere, using telescopes and space probes to gather data about its temperature, pressure, and chemical composition. However, a planet composed of dark matter would not have a traditional surface in the way that we understand it. Instead, it might be more like a cloud of dark particles, which makes studying its structure immensely difficult. To probe such a planet, scientists might need to develop entirely new methods for studying the interaction between dark matter and normal matter. This could involve theoretical models, computer simulations, and experimental work in particle physics labs. In a more speculative sense, non-baryonic planets could also present unique environments for the existence of life. If dark matter has properties that are fundamentally different from ordinary matter, it raises the possibility that life, in a form completely alien to anything we know, could exist on these planets. Perhaps life could arise from the interactions between dark matter and normal matter in ways that we cannot yet imagine. While this may sound like science fiction, the possibilities are endless, and as we push the boundaries of our understanding of physics, such ideas become more grounded in the realm of possibility. This brings us to another intriguing question. What would it mean for our understanding of life in the universe if non-baryonic planets were discovered? The search for extraterrestrial life has been a central focus of modern astronomy for decades. Most of our efforts have been concentrated on finding planets that are similar to Earth, with liquid water and an atmosphere that supports life as we know it. However, if non-baryonic planets exist, and if they could potentially harbor life in forms we cannot even comprehend, it would force us to rethink everything we know about biology, chemistry, and the conditions necessary for life. The implications for astrobiology would be profound. Currently, life is thought to require a stable environment with liquid water, a source of energy, and a variety of chemical elements such as carbon, nitrogen, and oxygen. But could life exist in a completely different environment, one where normal matter and dark matter interact in ways we don't yet understand? Could the dark matter that makes up a non-baryonic planet somehow form the foundation for life? It's impossible to say for sure, but the idea of life existing on a non-baryonic planet would open up a whole new field of astrobiological research, one that could radically change our understanding of the universe and our place within it. As we continue to look beyond the traditional boundaries of known planets and celestial objects, it's important to remember that the universe is vast and full of mysteries we are just beginning to understand. Non-baryonic planets are a perfect example of how our assumptions about the cosmos can be challenged by the unknown. Whether or not such planets exist, the pursuit of understanding them is a journey that will undoubtedly lead to new discoveries, new technologies, and new ways of thinking about the very nature of matter, energy, and existence itself. The search for non-baryonic planets is not just about uncovering a new type of planet. It's about pushing the limits of our knowledge, challenging our understanding of the universe, and exploring the fundamental building blocks of reality. In the coming years, as technology advances and our understanding of dark matter and other exotic forms of matter deepens, we may be on the cusp of one of the most groundbreaking discoveries in the history of science. As the quest for these mysterious worlds continues, the possibilities are boundless. We may find that the universe is even stranger and more complex than we ever imagined. And in doing so, we might discover new ways of thinking, new paradigms that could shape the future of science and humanity for generations to come. As our exploration into the realm of non-baryonic planets progresses, one of the key challenges we will face is distinguishing these planets from other phenomena in the universe. Non-baryonic planets may have characteristics that overlap with other celestial objects, such as brown dwarfs or rogue planets, which can further complicate detection efforts. Brown dwarfs, for instance, are objects that are too small to be considered full-fledged stars, but too large to be considered planets. While they don't emit much visible light, they still radiate some infrared energy, which makes them detectable. Rogue planets, on the other hand, are planets that don't orbit any star, instead drifting through the galaxy in isolation. While both brown dwarfs and rogue planets can appear to be similar to non-baryonic planets in certain ways, they are still composed of ordinary matter. The key difference with non-baryonic planets is that their very structure is based on exotic forms of matter, such as dark matter or other hypothetical particles. This means that any detection methods we use to explore them will need to be sophisticated enough to discern these differences. For instance, if a non-baryonic planet interacts with light in a way that we don't yet understand, it might be difficult to distinguish it from a rogue planet or other astronomical object unless we employ advanced techniques like gravitational lensing or gravitational wave detection. Gravitational lensing, a phenomenon where light from a distant object is bent around a massive object, could potentially offer a way to identify non-baryonic planets. If a non-baryonic planet is located in a region where its gravitational field can bend the light of a more distant star, astronomers may be able to spot its presence by analyzing the way the light is distorted. This method has been used to detect dark matter in galaxies and galaxy clusters, and it could potentially be applied to locating planets composed of dark matter as well. But even if we were able to detect non-baryonic planets using these sophisticated techniques, we would still be far from understanding their true nature. What would a planet made of dark matter look like? Would it have a core, an atmosphere, or even a surface? Given that dark matter doesn't interact with light or other forms of electromagnetic radiation in the same way as ordinary matter, it's likely that these planets would have an entirely different structure than anything we have encountered before. They might be nearly invisible, with only their gravitational effects revealing their existence. The lack of an observable surface could make studying them incredibly challenging, as we wouldn't have a traditional, planetary, environment to analyze. This brings us back to the importance of theoretical models. While we can't yet observe non-baryonic planets directly, we can create computer simulations and models that predict what such planets might look like based on our current understanding of dark matter and other exotic particles. These simulations could help scientists anticipate the characteristics of these planets, such as their size, mass, and gravitational pull, even if we can't observe them with our current instruments. Theoretical models could also help us design future missions and instruments that are specifically tailored to detect these types of planets. In fact, as technology continues to improve, we may begin to see advancements in the kinds of sensors we use to detect non-baryonic matter. For example, scientists are already working on creating ultra-sensitive detectors that can capture the faintest signals from dark matter particles. These detectors are designed to pick up interactions between dark matter and ordinary matter, which could provide the first concrete evidence of non-baryonic planets. The development of these technologies could revolutionize our ability to explore the cosmos and uncover hidden worlds that have remained undetectable until now. One of the more fascinating ideas associated with non-baryonic planets is their potential role in the larger cosmic structure. In our current understanding of the universe, galaxies are primarily composed of ordinary matter, while dark matter forms a vast, invisible web that influences the motion of galaxies and galaxy clusters. If non-baryonic planets exist, they could potentially be part of this larger cosmic structure. They might be scattered throughout the universe in regions dominated by dark matter, acting as dark satellites, orbiting dark stars or residing in dark nebulae. This raises the possibility that the distribution of dark matter in the universe could be more complex than we currently imagine. If non-baryonic planets are common in certain regions of space, they could contribute to the overall mass and gravitational structure of the cosmos in ways that we don't yet understand. They might even play a role in the formation of galaxies or the evolution of large-scale cosmic structures, further deepening the mystery of dark matter and its influence on the universe. The discovery of non-baryonic planets could also have profound implications for our understanding of the origins of the universe. As we study dark matter, we may begin to uncover clues about the formation of galaxies and the early moments of the cosmos. The presence of these planets could offer insights into the conditions that prevailed in the early universe, potentially shedding light on the processes that led to the creation of the first stars, planets, and galaxies. If non-baryonic planets are indeed a product of the same forces that shaped the universe in its infancy, they could hold valuable information about the fundamental physics that governed the Big Bang and the subsequent formation of the cosmos. As we continue to explore these strange, hypothetical worlds, it's important to keep in mind that the search for non-baryonic planets is still in its infancy. We are still developing the tools and techniques necessary to detect them, and much of what we know about them is based on speculation and theoretical models. However, the mere possibility that such planets exist opens up a new frontier in our understanding of the universe. The study of non-baryonic planets is part of a broader effort to understand the nature of dark matter and its role in the cosmos. While we have made significant strides in detecting dark matter's gravitational effects, we still don't know much about its composition or behavior. The discovery of non-baryonic planets could be a key step in unraveling these mysteries, offering us a glimpse into the hidden aspects of the universe that have remained out of reach for so long. As we continue to search for non-baryonic planets, we may also discover other exotic forms of matter that challenge our understanding of the laws of physics. The universe is vast and full of surprises, and as we explore deeper into the unknown, we may uncover phenomena that we can't even begin to imagine. Non-baryonic planets could be just one piece of the puzzle, one more mystery that beckons us to continue our quest for knowledge. The discovery of non-baryonic planets would not just be a scientific breakthrough, it would be a profound shift in our understanding of the universe. It would force us to rethink everything we know about matter, energy, and the very fabric of space-time itself. And in doing so, it would inspire future generations of scientists, explorers, and dreamers to reach further into the cosmos and uncover the secrets that lie beyond the stars. As we continue to delve into the possibilities of non-baryonic planets, it's worth considering the potential implications for our understanding of planet formation itself. Currently, the process of planet formation is based on the idea that planets form from the accumulation of matter, gas, dust, and rock around a young star. This model, known as the nebular hypothesis, has served as the foundation for our understanding of how planets like Earth and Jupiter came into existence. However, non-baryonic planets may challenge this model in ways that we have not yet fully considered. If these hypothetical planets are primarily composed of dark matter or some other non-baryonic substance, their formation might not follow the same rules as the formation of traditional planets. For example, instead of gathering up matter from a protoplanetary disk, non-baryonic planets could form through the accumulation of dark matter in regions of space where it is most dense. In this scenario, a non-baryonic planet might emerge in a completely different way, perhaps due to the gravitational collapse of dark matter itself, or the interaction of exotic particles that we have yet to discover. This raises the intriguing question of whether the same process that gives rise to stars and galaxies, gravitational collapse, could also give birth to non-baryonic planets. Gravitational collapse occurs when a region of space, whether it's a gas cloud or a clump of dark matter, becomes dense enough for its own gravity to pull the material together. In the case of stars and galaxies, this collapse leads to the formation of massive bodies that eventually ignite or form large-scale structures. Could dark matter undergo a similar collapse to form planets, albeit of a completely different nature than those composed of ordinary matter? The idea of non-baryonic planets emerging from gravitational collapse also opens the door to the possibility of these planets having vastly different environments and structures compared to those that form from baryonic matter. If dark matter plays a key role in their formation, these planets might lack the familiar features we associate with traditional planets, such as solid surfaces, atmospheres, and oceans. Instead, they could have an entirely alien makeup, one that defies the usual expectations of planetary bodies. To understand how non-baryonic planets could impact our current understanding of planetary systems, it is essential to consider the properties of dark matter itself. Dark matter is a mysterious substance that makes up about 27% of the universe's total mass, yet it has never been directly observed. Its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. While scientists have not been able to detect dark matter directly, they have confirmed its existence through its influence on the motion of galaxies and other large-scale structures. If non-baryonic planets are composed of dark matter, they would likely exhibit similar gravitational effects, such as the bending of light and the distortion of nearby space-time. These planets might not interact with electromagnetic radiation in the way that ordinary matter does, making them incredibly difficult to detect through traditional methods like optical telescopes or radio signals. This raises the possibility that many of these planets could be lurking undetected in the universe, hidden in the vast stretches of dark matter that permeate our cosmic neighborhood. The challenge of detecting non-baryonic planets also has implications for our broader understanding of the universe. If we are to discover these elusive objects, it will require the development of new observational techniques, sensors, and technologies. For example, scientists might need to focus on indirect methods of detection, such as studying the gravitational effects of these planets on nearby stars or galaxies. This could involve advanced gravitational wave detectors, which are capable of picking up minute distortions in spacetime caused by the motion of massive objects. Another intriguing avenue of exploration would be the use of neutrino detectors to search for interactions between non-baryonic planets and neutrinos, which are subatomic particles that are notoriously difficult to detect. Neutrinos are produced in vast quantities by the Sun and other stars, and their interactions with matter could provide us with important clues about the presence of non-baryonic objects in the universe. By studying how these particles interact with dark matter, scientists might be able to infer the location and properties of non-baryonic planets, even if they remain otherwise invisible to traditional methods of observation. Despite the challenges involved in detecting non-baryonic planets, the potential rewards of such a discovery would be astronomical. Finding evidence of planets made primarily of dark matter would not only revolutionize our understanding of planetary formation, but it would also provide crucial insights into the nature of dark matter itself. This, in turn, could lead to breakthroughs in other areas of physics, including the understanding of the fundamental forces that govern the universe. Furthermore, the discovery of non-baryonic planets would force us to rethink our assumptions about the diversity of planetary systems. Currently, we define planets based on their composition, structure, and behavior. But what if non-baryonic planets are so fundamentally different from ordinary planets that they do not fit into any of our existing categories? This would challenge our current classification schemes and force us to develop new ways of thinking about the range of possibilities that exist in the universe. If non-baryonic planets are indeed out there, they could also have important implications for the search for extraterrestrial life. While we have focused much of our search for life on planets that resemble Earth, those with liquid water, stable climates, and breathable atmospheres, non-baryonic planets might open up entirely new possibilities. If life can exist in environments that we have not yet considered, the discovery of such planets could greatly expand the scope of our search for life beyond Earth. The study of non-baryonic planets is also closely tied to broader questions about the fate of the universe. As we explore the mysteries of dark matter and exotic forms of matter, we are also grappling with the larger questions about the ultimate fate of the cosmos. If non-baryonic planets are part of the dark matter structures that dominate the universe, they could hold key clues about the long-term evolution of the universe itself. Are these planets a reflection of the universe's earliest moments? Or do they represent a future in which dark matter plays a more dominant role? The existence of non-baryonic planets could also shed light on the future of our own solar system. While we are currently focused on understanding the formation and evolution of planets made of ordinary matter, the discovery of non-baryonic planets could challenge our assumptions about how planetary systems evolve over time. Could dark matter play a role in the creation of new planets in the distant future? Or might these planets be remnants of a bygone era when the universe was in a different state? As we continue to push the boundaries of our knowledge, the study of non-baryonic planets offers a tantalizing glimpse into the mysteries of the cosmos. While we may not yet have the tools to detect these strange, hypothetical objects, the very possibility that they exist opens up a whole new realm of exploration. The discovery of non-baryonic planets would not only deepen our understanding of dark matter, but it would also inspire future generations of scientists and astronomers to explore the unknown and expand the horizons of human knowledge. The idea of non-baryonic planets, though still speculative, represents one of the most fascinating frontiers of modern astrophysics. As we continue to explore the nature of dark matter, exotic particles, and the formation of planetary bodies, we are not only uncovering the hidden aspects of the universe, but also challenging our very understanding of what it means for something to be a planet. Whether these planets are eventually discovered or remain the stuff of theoretical speculation, their potential existence invites us to rethink the universe in ways we have never before imagined. And who knows? In the future, we may find ourselves staring at a non-baryonic planet, a world beyond the bounds of our current understanding, forever changing the way we view our place in the cosmos. As the search for non-baryonic planets continues, it's crucial to consider the theoretical models that could guide us in understanding their potential existence. These models aren't just abstract thought exercises. They form the foundation of how we might eventually detect such planets, or even understand their behavior if we do find them. To date, most studies surrounding dark matter focus on its influence on large-scale structures like galaxies and galaxy clusters. But as we shift our attention toward the possibility of non-baryonic planets, our models of dark matter's behavior must evolve to account for the gravitational and physical properties that could lead to the formation of planets. Dark matter, unlike ordinary matter, interacts primarily through gravity and, potentially, weak nuclear forces. Unlike baryonic matter that forms dense, solid bodies like rocky planets, non-baryonic planets might have a more diffuse structure. Their internal compositions might not be uniform, instead consisting of dark matter particles that interact in ways we are still striving to fully comprehend. Given that dark matter is thought to be about 5 times more abundant than ordinary matter in the universe, the idea that some regions could accumulate enough to form planetary bodies is certainly plausible. While we haven't detected dark matter directly, scientists have developed several theoretical models for how it behaves on large and small scales. One of the most widely accepted theories is the idea of WIMPs, weakly interacting massive particles, which are hypothesized to make up dark matter. WIMPs, if they exist, would interact very weakly with normal matter and light, making them incredibly difficult to detect. But they would still exert gravitational influence, which could affect the formation and motion of planets composed largely of dark matter. Another theory involves axions, a different type of particle that could be responsible for dark matter. Axions are theorized to be extremely light, but they would also interact minimally with electromagnetic radiation, making them nearly impossible to observe with conventional telescopes. If axions are indeed responsible for dark matter, they might accumulate in large enough quantities to form dense objects that could act as planets. The nature of these planets would be incredibly strange, perhaps unlike anything we have imagined in conventional astronomy. Given the faint interaction between dark matter and electromagnetic radiation, non-baryonic planets might not exhibit the same visible characteristics as traditional planets. They wouldn't shine or reflect light in the way stars or gas giants like Jupiter do. Instead, they would likely be invisible to our eyes, detectable only by their gravitational effects on nearby objects. In this sense, their presence might be inferred from the way they affect the motion of nearby stars or the bending of light, in much the same way that we detect the presence of dark matter on a galactic scale. This opens up entirely new frontiers for detection, methods that rely on indirect measurements rather than direct observation. In the near future, we could see the development of increasingly sensitive instruments capable of detecting the subtle gravitational influences of non-baryonic planets. One such method could involve studying gravitational lensing, the bending of light from distant stars as it passes near a massive object. If a non-baryonic planet were present in a star system, it could distort the light from a background star, giving astronomers a clue that something unusual exists there. Such observations might not provide a full picture of what these planets are like, but they could be the first steps toward understanding how they interact with their environments. As we consider the potential locations of non-baryonic planets, it's important to note that they might not be confined to the regions of space we currently observe. Since dark matter is spread throughout the universe, and because its distribution is uneven, non-baryonic planets could be hidden in places where traditional telescopes can't easily detect them. These planets might even be located in the vast expanses of the intergalactic void, far from any stars or galaxies. In these regions, they would be surrounded by dark matter rather than light-emitting objects, making them nearly impossible to find through traditional astronomical methods. One of the more exciting aspects of the search for non-baryonic planets is the possibility that they might provide insight into the very nature of dark matter itself. Dark matter has long been one of the greatest mysteries in astrophysics. Although we can observe its gravitational effects on visible matter, we still do not know what dark matter is made of. Is it composed of WIMPs, axions, or something entirely different? By studying non-baryonic planets, we could gain new information about the properties of dark matter, helping us to solve one of the universe's most profound puzzles. Understanding non-baryonic planets could also have implications for the search for life in the universe. Although these planets would be very different from those composed of ordinary matter, it is possible that life could exist in some form on them. If life is based on different chemical or physical processes than what we currently understand, it's possible that non-baryonic planets might host forms of life that are completely alien to us. However, the absence of the kinds of environments that we associate with life, liquid water, solid surfaces, and an atmosphere, might suggest that life as we know it wouldn't survive on these planets. This could challenge our assumptions about where life can exist and how it might form. Beyond the search for life, the discovery of non-baryonic planets could have profound implications for our understanding of the universe's structure and history. If these planets exist, they may offer a glimpse into a different type of planetary formation than we have ever seen. As previously mentioned, traditional planet formation theories rely on the accumulation of gas, dust, and rock. But if non-baryonic planets are formed from dark matter, they might not follow the same patterns of growth. Instead, they could form in response to entirely different forces, governed by the unique properties of dark matter itself. Understanding this process would provide new insights into the variety of planetary systems that might exist in the universe, potentially revealing entirely new categories of planets that we haven't even conceived of yet. As we approach the limits of our current understanding, it's also important to acknowledge the potential risks and challenges that come with the discovery of non-baryonic planets. The strange and elusive nature of these planets means that we are still in the early stages of exploring their potential properties and behavior. There is much we don't yet know about how dark matter interacts with itself, let alone how it might give rise to planetary bodies. Any attempt to study these planets would require not only advances in observational technology, but also an entirely new framework for interpreting the data we collect. We might need to reconsider some of our most fundamental assumptions about how planets behave, or even redefine what we think of as a planet altogether. At the same time, there is no doubt that the discovery of non-baryonic planets would open up an entirely new chapter in the history of astronomy. As scientists begin to probe the possibilities of these planets, we may find ourselves confronting questions that go beyond the realms of physics and cosmology, and venture into the very nature of reality itself. What is the true nature of dark matter? How do non-baryonic planets interact with the rest of the universe? Can we ever fully understand these mysterious bodies, or are they destined to remain beyond our reach? In the coming decades, advancements in technology may allow us to begin answering these questions. From more sophisticated gravitational wave detectors to next-generation space telescopes, the tools we have at our disposal are constantly improving. These technological advancements will provide us with the means to explore the universe in ways that were previously unimaginable, allowing us to peer deeper into the cosmos and perhaps uncover some of its most elusive secrets. The existence of non-baryonic planets is still a hypothetical idea, one that could challenge our understanding of planets, dark matter, and the universe itself. Yet, the mere possibility of such planets forces us to confront the limits of our knowledge and the vast unknowns that still await discovery. Whether or not these planets exist, the pursuit of understanding them will continue to push the boundaries of science and open new avenues for exploration. As we strive to unravel the mysteries of dark matter, we might just find that the universe holds far more than we ever imagined, and that our place in it is far more mysterious than we ever realized. As we continue to explore the possibility of non-baryonic planets, it's essential to also consider the broader implications of their discovery, especially in terms of our understanding of the universe. One of the most intriguing aspects of these hypothetical planets is their potential to reshape our entire view of cosmology. For decades, we have relied on the conventional understanding that planets are made of ordinary matter, atoms, molecules, and elements that we can observe and study. The introduction of non-baryonic planets into this equation would not only challenge our understanding of what planets are but could also force us to rethink our assumptions about how the universe functions at its most fundamental level. For instance, one question that arises when considering the potential existence of non-baryonic planets is whether they might form in ways that we have not yet considered. Traditional planet formation models, which involve the accumulation of dust, gas, and solid matter under the influence of gravity, might not be applicable in the case of non-baryonic planets. Instead, these planets could form in response to different forces that are tied directly to the properties of dark matter itself. If this is the case, we might need to develop entirely new theories of planetary formation, theories that take into account the unique characteristics of dark matter and how it interacts with itself. Moreover, the discovery of non-baryonic planets could also prompt us to reconsider our understanding of the forces that govern the universe. Gravity, as we know it, would still play a role in the behavior of these planets, but it may not be the only force at work. Dark matter may have its own set of interactions that we are not yet aware of, and these interactions could have profound effects on the structure and behavior of non-baryonic planets. This could lead to a more nuanced understanding of how the fundamental forces of the universe operate, opening up entirely new areas of research that could lead to groundbreaking discoveries. Another significant implication of discovering non-baryonic planets is the impact it could have on our understanding of the distribution of matter in the universe. Currently, dark matter is known to exist in large quantities throughout the cosmos, and its gravitational effects are seen in the way galaxies rotate, the way galaxy clusters behave, and the way light bends around massive objects. If non-baryonic planets were discovered, it would suggest that dark matter is not only present in these large-scale structures but could also exist in smaller, more localized objects. This could change our perception of how dark matter is distributed throughout the universe, suggesting that it is far more widespread than we previously thought. Furthermore, the discovery of non-baryonic planets could also shed light on the origins and evolution of dark matter itself. While much of our current understanding of dark matter comes from its indirect effects on visible matter, the potential to study non-baryonic planets could provide a more direct way to probe the properties of dark matter. This could help answer some of the most fundamental questions about dark matter's nature, such as what it is composed of, how it behaves on small scales, and whether it could have played a role in the formation of the early universe. Such discoveries could transform our understanding of the cosmos, helping us to piece together the history of the universe in a way that is currently beyond our reach. As we think about the possibility of non-baryonic planets, it's important to recognize the limitations of our current technology and the challenges that lie ahead in detecting these elusive objects. Since non-baryonic planets are hypothesized to be made primarily of dark matter, they would not emit or reflect light in the same way that ordinary planets do. This makes them incredibly difficult to observe directly, as our traditional methods of detection, such as optical telescopes or radio telescopes, rely on the ability to detect electromagnetic radiation from the objects we study. In the absence of direct detection methods, scientists are developing new techniques to observe the gravitational effects of non-baryonic planets. One promising approach involves using gravitational microlensing, a phenomenon in which the gravitational field of an object, such as a planet, bends the light from a distant star. If a non-baryonic planet passed in front of a distant star, it could cause a temporary brightening of the star's light, providing a telltale signature of its presence. While this technique has already been used to discover exoplanets made of ordinary matter, it could also be employed to detect non-baryonic planets, provided that we can identify the subtle differences between the two types of objects. In addition to gravitational microlensing, other methods, such as gravitational wave detection, may also hold promise for identifying non-baryonic planets. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, and they can be detected by extremely sensitive instruments such as the Laser Interferometer Gravitational Wave Observatory, LIGO. If non-baryonic planets exist, their motion and interactions could generate gravitational waves that might be detectable by these instruments. However, this would require advances in technology and a much deeper understanding of how dark matter interacts with ordinary matter. One challenge in studying non-baryonic planets is that their very nature could complicate our ability to interpret the data we gather. Since we have little experience with objects that are primarily composed of dark matter, we can't be sure how they might behave or what kind of signals they would produce. Would they have the same gravitational effects as ordinary planets? Would they interact differently with nearby stars and other objects in their systems? These are questions that scientists will need to answer as they develop new models and techniques for detecting and studying non-baryonic planets. While the search for non-baryonic planets remains speculative at this stage, it is an exciting area of research that could lead to major breakthroughs in our understanding of the universe. The study of dark matter, one of the greatest mysteries in modern physics, could offer profound insights into the nature of the cosmos and our place within it. The possibility that planets could form from dark matter would not only expand our definition of what a planet is but could also provide a window into the mysterious and largely invisible realm of dark matter that shapes the structure of the universe. As astronomers and physicists continue to push the boundaries of knowledge, we may one day find that non-baryonic planets are not just a theoretical curiosity, but an actual class of celestial objects that exist in the far reaches of the cosmos. The discovery of such planets would revolutionize our understanding of planetary systems and dark matter, providing answers to some of the most profound questions in astrophysics. Whether we are ready for such a discovery or not, it is clear that the search for non-baryonic planets is a journey that will lead us into uncharted territory, challenging everything we know about the universe. We would be forced to ask whether dark matter interacts with itself in complex ways, perhaps even forming bound states or exotic matter configurations that can cluster and stabilize into coherent, planet-sized objects. If so, these interactions might mimic, in a completely different realm of physics, the same kinds of behaviors we see in baryonic matter: gravitational aggregation, structural stability, and even thermodynamic properties, albeit through mechanisms far removed from the atomic forces that bind our familiar matter together. This opens up a realm of theoretical inquiry into the possibility that dark matter is not merely a passive gravitational actor, but a dynamic and complex component of the cosmos capable of forming structured systems. In such a reality, non-baryonic planets could exist in large numbers, possibly even dwarfing the number of ordinary planets. They might cluster around dark matter-dense regions in galactic halos, orbit black holes unseen by our instruments, or even pass through baryonic planetary systems, undetectable except for their gravitational influence. These possibilities stretch the limits of our observational capabilities. Conventional detection methods, such as transit photometry, radial velocity measurements, or direct imaging, are entirely ineffective when it comes to something that emits no light, absorbs no radiation, and interacts only weakly with known particles. This means we may need to invent new forms of astronomical instrumentation specifically designed to detect gravitational anomalies, lensing signatures, or other indirect indicators of massive but invisible planetary bodies. One promising avenue of detection is gravitational microlensing. This method relies on the bending of light from a distant star as a massive object passes between it and the observer. Even if the intervening object is dark and emits no radiation, it still warps the fabric of space-time enough to magnify and distort the light from the background source. Non-baryonic planets, if massive enough, could be detected using this method, though distinguishing them from rogue baryonic planets would remain an immense challenge. Adding another layer to this speculative puzzle is the idea that non-baryonic planets may not be entirely dark. While dark matter itself doesn't emit light, the presence of trace amounts of baryonic matter, trapped in a gravitational well dominated by dark mass, could theoretically give off radiation or interact with surrounding environments in unique ways. For example, friction between trapped gas and dark matter-induced gravity might heat the gas, leading to emissions detectable in radio, X-ray, or infrared bands. Such hybrid systems might serve as breadcrumbs pointing us toward entirely dark cores. Another critical implication of non-baryonic planets is the question of habitability, not in the conventional sense of supporting life as we know it, but rather the question of whether they could harbor unknown forms of matter-based complexity. If dark matter can clump into planet-sized objects, and if it has its own unique spectrum of particles and forces, it raises the fascinating speculation: could dark chemistry exist? Could self-organizing systems form within non-baryonic matter, analogous to molecular networks, capable of complexity, computation, or even life, albeit life utterly alien and undetectable by current methods? This is speculative in the extreme, but not without precedent in theoretical frameworks. Just as baryonic matter forms atoms, molecules, and biological systems through electromagnetic interactions, it's conceivable that dark matter could have analogous interactions governed by a dark electromagnetism, or other unknown force. In such a scenario, non-baryonic planets could be more than inert masses. They could be worlds unto themselves, structured, dynamic, and perhaps hosting their own version of natural evolution. Even from a purely physical standpoint, non-baryonic planets offer new frontiers for understanding matter distribution in the universe. If they exist in significant numbers, they may account for discrepancies in galactic rotation curves or contribute to the unexplained gravitational effects that scientists currently attribute to diffuse halos of dark matter. In this light, non-baryonic planets wouldn't just be a curiosity, they could be a key component of galactic architecture, influencing star formation, spiral arm dynamics, and halo structures. The implications even ripple into the field of quantum mechanics. Many dark matter candidates, such as axions, have quantum properties that could lead to macroscopic quantum states. If enough of these particles coalesce into a stable structure, it could potentially form a Bose-Einstein condensate, a state of matter where particles occupy the same quantum state and behave as a single quantum entity. Imagine a planet-sized body composed entirely of such a state, its mass exerting gravity on surrounding space, yet its internal behavior governed by quantum superposition and entanglement on a colossal scale. The implications for quantum gravity, decoherence, and even quantum information theory would be groundbreaking. Non-baryonic planets also pose challenges to how we model planetary interiors. Without atomic nuclei and electrons forming atoms, there would be no crust, mantle, or core in the traditional sense. Instead, internal pressure and density would be governed by completely different rules, perhaps determined by the mass and spin of dark matter particles, their annihilation rates, or some other, as yet unknown quantum pressure. Because of this, these objects might be able to achieve much higher mass-to-radius ratios than ordinary planets. Their gravitational fields might be steeper, sharper, and more compact, potentially mimicking the gravitational signature of black holes or neutron stars, but without the same event horizon or nuclear processes. This blurring of boundaries between dense exotic matter and more diffuse forms of invisible mass may require entirely new classifications of celestial bodies, beyond planet, star, or black hole. Furthermore, with future advancements in space-based observatories like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission, our sensitivity to gravitational lensing phenomena will increase dramatically. These instruments are designed to probe the dark universe, mapping the distribution of dark matter, tracking cosmic acceleration, and detecting subtle distortions in space-time. With their enhanced resolution and wider observational fields, they could help us uncover not just the presence of dark matter in bulk, but individual non-baryonic structures masquerading as ghost planets across the galaxy. The very idea that planets might exist completely hidden from our view, moving silently through space, leaving only gravitational ripples in their wake, is more than just an academic curiosity. It forces a re-examination of how we define a planet. Traditionally, a planet is described based on its ability to orbit a star, maintain hydrostatic equilibrium, and clear its orbital neighborhood. But these criteria are rooted in our understanding of luminous matter. If a dark matter clump can form a stable, orbiting massive body, should we not consider it a planet as well, even if it is composed entirely of non-baryonic material? This conceptual shift could alter planetary science in profound ways. Non-baryonic planets might be cold, structureless masses, or they could be something far stranger. It's possible that, depending on the nature of dark matter, these objects could have internal processes, gravitational stratification, or quantum states that differ completely from anything we've seen. Their surfaces might not even be solid in the conventional sense. They could be fluid-like, gelatinous, or exhibit strange phase transitions at scales that are entirely alien to human experience. Speculation doesn't stop there. Some theories suggest that non-baryonic planets might be completely impervious to radiation, meaning they could pass through star systems unaffected by stellar winds or magnetic fields. Others propose that they might even be stable in environments that would utterly destroy a normal planet, such as within the accretion disk of a black hole or deep inside intergalactic voids. The fact that they don't interact electromagnetically also means that they would be invisible to infrared or X-ray telescopes, totally black against the blackness of space. If such objects exist, then it's very likely they are not evenly distributed. We might find dark matter forming halos around galaxies, but if it can condense under certain conditions, there could be dense pockets where non-baryonic planets cluster in hidden systems, perhaps even forming dark solar systems, orbiting a non-luminous dark matter star. These invisible star systems could have their own architectures, their own dynamics, and potentially their own forms of organization or structure that we cannot yet imagine. Now, here's where the speculation gets truly mind-expanding. If dark matter is capable of organizing into stable planetary forms, could it also form life? While this is currently the domain of highly theoretical astrophysics and speculative astrobiology, it's worth considering. Life as we know it depends on baryonic chemistry. But what if there are forms of organization or computation that could arise purely through gravitational interactions or unknown dark sector forces? In such a reality, entire ecosystems or information processing entities could exist, completely hidden from our senses and instruments. Imagine a non-baryonic planet with a layered interior structure, not formed by pressure and molten rock like Earth, but perhaps shaped by exotic forces such as self-interacting dark matter or unknown quantum pressures. These layers might not follow the logic of crust, mantle, and core. Instead, they could feature fluctuating densities, liquid like dark matter pools, or even zones of rapid phase change triggered by temperature or pressure thresholds we cannot yet comprehend. Some models suggest that if dark matter can cool and collapse under gravity, then these non-baryonic planets might have distinct temperature gradients. This could give rise to processes vaguely analogous to weather, albeit on an entirely different scale and substance. Instead of water cycles or carbon-based clouds, these planets might experience strange flows of dark particles, governed by interactions so faint they are undetectable to current instruments but crucial to the planet's internal balance. The presence of such objects would revolutionize our understanding of cosmic evolution. It raises the question, could non-baryonic planets have formed earlier than baryonic ones? Since dark matter dominates the mass of the universe and doesn't interact with radiation, it wasn't hindered by the same early universe processes that delayed the formation of stars and galaxies. In theory, dark matter clumps could have coalesced into stable objects, perhaps even dark planets, well before the first baryonic atoms came together. If that's true, the oldest planets in the universe might not be rocky, metallic spheres orbiting stars, but silent, unseen masses drifting in the cosmic void, ancient relics from an era before light itself. These would be true primordial objects, forged in the first minutes after the Big Bang, when dark matter had already begun shaping the scaffolding of cosmic structure while baryonic matter lagged behind. Such an idea radically reorders our cosmic timeline. It means that baryonic matter, everything we see, touch, and measure, may simply be a latecomer in a universe where dark matter laid the foundation. The galaxies, stars, and planets we observe might merely be the decorations on an invisible structure shaped billions of years earlier by dark forces. The implications for cosmology are enormous. It would mean that for every baryonic planet we catalog, there could be dozens, hundreds, or even thousands of non-baryonic counterparts lurking in the dark, each with its own mysterious history. This scenario also raises intriguing possibilities about interactions between dark and baryonic objects. Could a non-baryonic planet pass through a baryonic one? Since dark matter interacts primarily through gravity and not electromagnetism, in theory, such a passage might be nearly seamless, like a ghost drifting through a wall. The gravitational effects would be noticeable, of course, localized disruptions, seismic tremors, or orbital anomalies. But visually and materially, there might be no trace at all. We might never know it had happened, save for unexplained shifts in gravitational behavior. Such events could even explain some anomalies in our solar system, peculiar tilts, eccentric orbits, or unexpected heat signatures. Perhaps a non-baryonic planet passed near or through a region of space, disturbing things just enough to confuse astronomers but never leaving a visible trail. If our current models don't include this possibility, we may be misinterpreting a variety of phenomena as quirks of conventional physics when they're actually evidence of hidden dark objects silently influencing the baryonic world. This opens yet another door. What if non-baryonic planets aren't completely isolated? Could they capture baryonic material over time, forming hybrid planets with dark matter cores and visible shells? Or might some cosmic environments, like the edges of galaxy clusters or dense dark matter halos, host a spectrum of mixed composition objects, ranging from pure dark matter bodies to strange planetary hybrids never before imagined? If such objects exist in large numbers, they might even account for part of the missing mass in galaxies, mass that gravitational models demand but remains undetected by electromagnetic observations. In galaxy rotation curves, where the speed of stars and gas doesn't drop off with distance from the galactic center as expected, dark matter has been invoked as the invisible glue holding everything together. Traditionally, this has been envisioned as a diffuse halo, but what if part of that mass resides in compact, planet-sized clumps? The implications would be profound, reshaping how we distribute and model dark matter in both galactic and intergalactic scales. These non-baryonic planets wouldn't emit light, wouldn't reflect light, and wouldn't radiate heat in any way we currently understand. They'd be black on black, silent in silence. The only sign of their presence might be an unexplained tug on a star's motion, or a brief lensing of light from a distant background source. Yet despite their invisibility, their mass would be just as real, their gravitational influence just as potent. This paradox, of something utterly undetectable by light, yet undeniable in its physicality, lies at the very heart of the mystery of non-baryonic matter. Now consider this. What if non-baryonic planets are not merely lifeless, inert clumps of matter? While it may sound like science fiction, it's worth pondering whether these exotic worlds could harbor forms of complexity, perhaps even consciousness, that emerge under physics we do not yet grasp. After all, our understanding of life is grounded in biochemistry and carbon-based molecules, all of which rely on electromagnetic interactions. But if there's a hidden sector of physics governing dark matter, there's nothing to say it couldn't support its own analogs to information storage, energy transfer, or organization. In such a scenario, a non-baryonic planet might evolve processes similar in spirit to weather systems, magnetic fields, tectonics, or even computation, but all mediated by unknown forces and particles. The internal workings of such a planet would be invisible to any telescope, unresponsive to any probe, yet potentially rich with interactions and complexities that rival or exceed anything in the visible universe. If dark matter has its own interactions, its own rules, then perhaps entire ecosystems of structure, order, and evolution are taking place right under our cosmic noses. More conservatively, though still wildly profound, is the idea that non-baryonic planets might serve as seeds or anchors around which baryonic matter later coalesces. In this model, dark matter clumps act like invisible scaffolds, drawing in gas and dust through gravity and providing the gravitational foundation for planet formation. It would suggest that even the familiar, rocky worlds of our solar system might owe their existence to an underlying, hidden architecture of dark matter. This dual-layered model of planet formation would dramatically alter our theories of solar system genesis. Interestingly, this idea isn't entirely incompatible with current simulations. In cosmological models of structure formation, dark matter collapses into halos long before baryonic matter begins to form stars or planets. The idea that smaller, denser clumps, potentially planetary in scale, could form early on and persist to this day is not only plausible, but expected under certain conditions. If we can refine our detection methods, these clumps could become the missing puzzle pieces in both dark matter mapping and planetary science. There's also the question of location. Where would these non-baryonic planets most likely reside? One hypothesis suggests they'd be concentrated in the outer halos of galaxies, far from the blinding light of galactic cores, where gravitational lensing surveys could more easily detect their influence. Another possibility is that they float freely through intergalactic space, remnants of dark matter substructures that never merged into larger galactic halos. Their dispersion might be utterly random, or subtly ordered by gravitational filaments woven across the cosmic web. And what of our own solar system? Could there be a non-baryonic planet lurking beyond the Kuiper belt or even further, cloaked in gravitational silence? It's a tantalizing idea. Some models propose that anomalies in the orbits of distant trans-Neptunian objects might hint at the gravitational influence of an unseen planet. While many scientists favor the idea of a baryonic planet night, there's room to ask whether the anomaly might instead be caused by a non-baryonic mass, one that doesn't reflect sunlight, doesn't emit heat, but exerts a subtle gravitational pull on everything around it. Detecting such an object would require immense precision. Traditional methods, like measuring reflected sunlight or emitted infrared radiation, are useless. We need to rely on precise orbital modeling, gravitational perturbations, or perhaps even direct observation of lensing effects in background starlight. It would be one of the greatest challenges in observational astronomy, yet the reward, a confirmed sighting of a non-baryonic planetary object, would be revolutionary. Such a discovery would also pose philosophical questions. What does it mean to see something in the cosmos? We often equate visibility with existence, but non-baryonic planets would shatter that assumption. They would exist wholly outside of our usual senses, invisible yet undeniably real. This shift in perception would be akin to the discovery of radio waves or X-rays, new layers of reality opening up before us, expanding the boundaries of what is scientifically knowable. On the theoretical side, particle physicists continue to develop models of dark matter that might permit the formation of compact structures. Some candidates include weakly interacting massive particles, WIMPs, sterile neutrinos, or axions. Each of these comes with its own implications for how dark matter clumps together, how it behaves under gravity, and whether it could form stable, planet-sized objects. Some models even suggest that self-interacting dark matter could coalesce into complex bodies more easily than non-interacting types. This leads us to an important point. The study of non-baryonic planets is a multidisciplinary endeavor. It touches on astrophysics, cosmology, particle physics, and planetary science. It requires theorists to imagine new physics, and observational astronomers to develop ingenious new methods. It challenges engineers to build more sensitive instruments, and data scientists to mine vast datasets for subtle signals. The search for these hidden worlds is one of the most collaborative and cutting-edge efforts in modern science. And it's not just about planets. The existence of non-baryonic planets suggests a whole hidden cosmos, a dark sector that could include stars, galaxies, and maybe even black holes made entirely from dark matter. If that's the case, then the visible universe is just a small part of a much larger, richer, and more complex multiverse of structure. Our telescopes only scratch the surface. The true architecture of the cosmos might be one of dualities, light and dark, seen and unseen, baryonic and non-baryonic. In this view, we live not in one universe, but in two intertwined realities, one glowing with starlight, the other cloaked in shadow. And somewhere in that shadow, vast worlds drift in silence. Non-baryonic planets, if they exist, are the first keys to unlocking this parallel domain. They may not shine, they may not speak, but their gravity sings a song that, if we listen closely enough, could reveal an entirely new chapter in the story of existence. In such a scenario, dark planets might not be barren at all. Instead, they could host intricate ecosystems made entirely of non-baryonic matter, with life forms evolving according to rules beyond our current comprehension. These wouldn't be alien in the conventional sense. They would be fundamentally unknowable, invisible to all traditional sensors, living in a universe parallel to ours, layered atop the same physical space but never interacting except through gravity. It's a sobering thought. The cosmos might be teeming with dark life, and we never even know. The idea that non-baryonic planets could harbor entire civilizations or ecosystems forces us to reconsider the very definition of a planet. Historically, a planet is a celestial body that orbits a star, is spherical due to self-gravity, and has cleared its orbital path. But these criteria are rooted in observable physics. Non-baryonic planets may not orbit stars at all. They might exist freely, gravitationally untethered, dark wanderers adrift in intergalactic space. Their sphericity might be governed by forces we can't measure, and their cleared orbit irrelevant in a realm of invisible interactions. Gravitational lensing remains one of the most promising tools for detecting such objects. When a massive body passes between Earth and a distant light source, like a quasar or galaxy, the gravitational field of the object bends and magnifies the background light. This phenomenon, known as microlensing when caused by planet-sized objects, has already been used to discover rogue planets in our own galaxy. If we begin seeing more microlensing events without corresponding luminous bodies, it may hint at the presence of dark matter planets. The size of these objects is also up for speculation. While the term planet suggests a scale similar to Earth or Jupiter, non-baryonic planets might range from asteroid-sized clumps to supermassive titans dwarfing any planet we've ever seen. Without radiation pressure or stellar heat to define their boundaries, these dark masses could be as dense or diffuse as the nature of dark matter allows. Some could even collapse into black hole-like states if conditions permit. Singularities formed not from stellar death but from exotic mass concentrations in the early universe. There is also the question of formation. In the early universe, baryonic matter was hot, ionized, and tightly coupled with radiation. It took hundreds of thousands of years for it to cool enough to form neutral atoms and later condense into stars and planets. But dark matter, which does not interact with radiation, could have begun clumping far earlier. These early clumps, born in the densest regions of the dark matter distribution, might have compacted under their own gravity into stable configurations. Over billions of years, they could have matured into what we now speculate to be non-baryonic planets. These planets might not have atmospheres in any traditional sense, but they could have layers of dark matter particles that behave fluidly under certain temperatures and pressures. Perhaps they exhibit weather-like phenomena caused by density waves or dark particle flows, forming invisible storms and circulation systems. In such environments, structures could emerge, similar to atmospheric bands on Jupiter or polar vortices on Earth, driven not by heat but by unknown forces. The role of entropy in these systems is particularly intriguing. In thermodynamics, entropy governs the arrow of time and the evolution of complexity. If dark matter operates under similar principles, then entropy would guide the structure and behavior of non-baryonic planets. They could develop thermal gradients, complex phase transitions, or even dark equivalents of tectonic activity as internal energy seeks equilibrium. These planets might quake, shift, or pulse with dark energy cycles beyond our capacity to detect. There's also the possibility that dark matter isn't a single type of particle, but a spectrum of particles with varying properties. In this framework, non-baryonic planets could develop strata, layers of different dark matter species sorted by mass, interaction strength, or some entirely unknown parameter. This stratification could create zones of interaction or turbulence, not unlike the way Earth's mantle behaves under stress. Imagine a dark planet undergoing a slow, invisible eruption of particles due to internal stress release, completely undetectable, yet as real and powerful as a volcanic eruption here on Earth. Some theories even suggest that dark matter might decay or transition into different states over cosmological timescales. If that's true, then non-baryonic planets might evolve, growing more massive, more compact, or more diffuse over time. Their gravitational signature would change slowly, altering the orbits of nearby stars or clusters. Entire regions of space could be subtly reshaped by these ghostly planetary shifts, without a single photon ever betraying the cause. Now consider the potential for these objects to collide. If two non-baryonic planets were to pass close enough for their gravitational fields to interact significantly, what would happen? Would they merge, bounce, disrupt one another into clouds of exotic matter? These events could produce ripples in spacetime, gravitational waves, just like black hole or neutron star collisions. Future gravitational wave detectors, tuned to new frequencies, might catch whispers of these collisions, offering indirect evidence of their existence. The idea that non-baryonic planets could act as seeds for galaxy formation is another tantalizing line of thought. In the early universe, dense pockets of dark matter served as gravitational wells, pulling in baryonic gas and giving rise to galaxies. But what if some of those pockets didn't form galaxies, but instead stabilized into planet-like objects? There would be cosmic orphans, failed galaxies, so to speak, now drifting alone, their gravitational roles played out, but their mass still very real. On a more speculative note, there are proposals that dark matter may form Bose-Einstein condensates on cosmic scales. In such a state, particles behave as one coherent quantum entity, losing their individuality. If non-baryonic planets are made of such condensates, they might exhibit quantum behaviors at macroscopic scales, something completely foreign to anything we've observed in planetary science. Their surfaces could blur, their internal dynamics could be probabilistic, and they might respond to gravitational fields in non-classical ways. One of the most challenging aspects of studying these hypothetical objects is the complete absence of electromagnetic interaction. With no heat signature, no light reflection, and no absorption or emission lines, we're effectively blind. Our best hope lies in gravitational studies, microlensing, orbital anomalies, and gravitational wave detections. Future missions like the Nancy Grace Roman Space Telescope or advancements in LISA, Laser Interferometer Space Antenna, could provide the tools to identify these dark ghosts indirectly. The philosophical implications are equally staggering. Non-baryonic planets challenge the anthropic principle, the idea that the universe must be the way it is to allow for observers like us. If there's an entire shadow realm of complex objects and possibly life that we cannot observe, then our current understanding of the universe is partial at best. We may be just one layer of reality, unable to perceive other equally intricate domains governed by unfamiliar physics. As the search for dark matter intensifies, the hypothesis of non-baryonic planets remains a frontier, one that straddles the border between physics and imagination. Every new gravitational anomaly, Every unexplained microlensing event, every faint signal from the cosmos might be the first whisper of these invisible worlds. As we develop more sensitive instruments and more sophisticated models, we may one day confirm their existence, not by seeing them, but by tracing their gravitational fingerprints across the cosmic tapestry. As we push further into the unknown, it is critical to consider the broader implications of non-baryonic planets on our understanding of the cosmos. If these objects do exist, it could mean that there are entire regions of the universe teeming with unseen planets, stars, and possibly even dark life forms. This realization challenges the very foundations of astrophysics and cosmology, suggesting that the universe is far more complex than we could have ever imagined. Dark matter, by its very nature, does not emit or interact with light in any measurable way. This is why it is so difficult to study. However, we do know that dark matter exerts gravitational influence, and this gravitational pull is something that can be measured. If non-baryonic planets are indeed out there, they could provide us with indirect clues about the distribution and properties of dark matter. By observing the gravitational effects of these objects on nearby stars, galaxies, and other celestial bodies, scientists may be able to piece together a more complete picture of dark matter's role in the universe. One of the most exciting possibilities is the role that non-baryonic planets could play in the formation of galactic structures. Dark matter is thought to be a key ingredient in the formation of galaxies, as it helps provide the necessary gravitational pull to bind large amounts of normal matter together. If non-baryonic planets exist, they could act as the building blocks for more complex structures, slowly coalescing over time into larger dark matter clumps, or even contributing to the formation of dark matter halos around galaxies. The idea that dark matter could give rise to complex, planet-sized objects also opens up a new frontier in the search for extraterrestrial life. While we have yet to find definitive proof of life elsewhere in the universe, the possibility of dark matter-based life forms presents an entirely new paradigm for thinking about the nature of life itself. These hypothetical life forms might not rely on carbon, water, or the elements we associate with life as we know it. Instead, they might thrive in conditions entirely foreign to us, using dark matter or other exotic forms of energy to fuel their processes. Another fascinating aspect of non-baryonic planets is the potential for them to have entirely different physical properties than the planets we are familiar with. Since they are composed of dark matter, their gravitational interactions might differ significantly from those of ordinary planets. Their internal structure could be vastly different as well, with layers of dark matter particles that behave in strange and unpredictable ways. For example, the core of a non-baryonic planet might experience different types of pressure and temperature conditions than the cores of normal planets, leading to the possibility of unique geological or atmospheric phenomena. Moreover, if these planets are not tied to stars and instead drift through space, they could exhibit behavior unlike anything we see with conventional planets. They might wander through interstellar space, unaffected by the radiation and heat that stars provide, existing in a cold, dark state. This opens up new questions about how they form, how they interact with their environment, and how they might evolve over time. Perhaps these rogue planets could be the remnants of ancient cosmic structures that were once part of larger galactic systems but were ejected into the void by gravitational forces. The lack of a star to provide energy for non-baryonic planets might also result in strange and unknown energy sources. Without the typical heat and light from a star, these planets might rely on dark energy or some other form of exotic radiation to maintain their internal dynamics. This could lead to entirely new forms of energy generation and utilization, giving rise to complex systems of interactions that we are not yet capable of fully understanding. The potential discovery of non-baryonic planets would not only change our view of the universe but also challenge our understanding of the fundamental forces of nature. Currently, we understand gravity, electromagnetism, and the strong and weak nuclear forces as the four fundamental forces that govern all matter. But the existence of non-baryonic planets could hint at additional forces at play, ones that are still hidden from us. These forces could be responsible for the behavior of dark matter, and by studying how they interact with visible matter, we might be able to unlock entirely new dimensions of physics. Furthermore, the discovery of such planets would significantly impact our search for extraterrestrial intelligence. If life can exist in forms completely different from anything we've imagined, based on dark matter or some other exotic substance, then our search for life in the universe might need to be redefined. The conventional methods of searching for habitable exoplanets, based on the assumption that life requires liquid water and certain chemical conditions, might not be applicable to dark matter-based life. As a result, future missions and telescopes may need to be designed with entirely new approaches in mind. One of the most intriguing questions posed by the existence of non-baryonic planets is whether these objects could have their own form of habitability, or even intelligent life. We often think of life as requiring a stable environment with a reliable energy source, such as a star, but dark matter could offer a completely different foundation for life. If dark matter has the ability to form complex structures, it might also allow for the development of sophisticated systems. These systems could mimic the complexity of life as we understand it, but with the added twist that they operate under rules entirely alien to our current understanding. Given the vastness of the universe, it's possible that non-baryonic planets are not just rare anomalies, but a fundamental part of the cosmic landscape. Perhaps every galaxy has its own population of these dark, invisible planets, silently orbiting stars or drifting through the cold void of intergalactic space. If this is the case, then the universe may be far more diverse than we ever imagined, full of hidden worlds that we can only begin to understand. The challenges involved in studying these objects are immense. Detecting dark matter, let alone planets made of it, is no small feat. The best tools we currently have at our disposal, microlensing, gravitational wave detectors, and radio telescopes, may one day reveal these objects, but we're still in the early stages of exploring this new frontier. As technology advances, however, and our understanding of dark matter deepens, we may one day uncover a whole new class of planets that will change everything we thought we knew about the universe. The potential of non-baryonic planets to reshape our understanding of the universe is enormous. Whether they remain a distant hypothesis or become an integral part of future discoveries, these objects force us to rethink the very nature of what a planet can be. The fact that they are composed of a substance that we cannot directly observe makes them even more mysterious and captivating. As our scientific tools become more sophisticated, we may one day peer into the darkness and uncover a hidden world that has been right under our noses all along. As we continue to probe the mystery of non-baryonic planets, it's important to consider the many implications their existence would have not just on science, but on our philosophical and existential outlook. Humanity has always sought to understand its place in the universe, often through the lens of what is familiar: planets made of ordinary matter, stars that shine brightly in the sky, and life forms that breathe oxygen. But if non-baryonic planets exist, they force us to reconsider what is possible and what we have defined as life, or even habitat. One of the most compelling aspects of non-baryonic planets is their ability to challenge our assumptions about the necessity of stars for planetary systems. In our solar system, planets orbit stars, relying on the energy and warmth provided by the sun. But if non-baryonic planets are out there, their existence without a star could indicate that planets do not necessarily need to be tied to stars for their formation or survival. They could remain in the dark void of space, shielded from the heat and light of a sun, thriving under conditions that are completely foreign to us. If this is true, then the question arises, what else in the universe could thrive in the absence of a traditional energy source? Could other forms of life be supported by forces or particles that are currently beyond our understanding? Could non-baryonic life forms exist on these planets, living under conditions we would consider inhospitable or downright impossible? If these questions seem far-fetched, it's worth remembering that our understanding of life on Earth has evolved dramatically over the centuries. Organisms that once seemed improbable, such as extremophiles, which survive in boiling acid lakes or the frozen extremes of Antarctica, are now seen as testament to the resilience of life in the most unexpected environments. Non-baryonic planets could open the door to a whole new class of extremophiles that exist not in extreme heat or pressure, but in the presence of dark matter or other exotic conditions. These thoughts lead us to an even deeper inquiry into the nature of matter and energy itself. We tend to think of the universe in terms of matter that we can detect, measure, and observe. But dark matter, by definition, remains invisible to all but its gravitational effects. As a result, non-baryonic planets, if they exist, offer us a glimpse into a realm of the universe that is completely out of sight, yet undeniably present. They represent a realm where our conventional understanding of physics, chemistry, and even biology could be turned upside down. Our current models of the cosmos, which are based on observable, baryonic matter, may only be a fraction of the full picture. What if the true nature of the universe is far more layered and intricate than we could have ever imagined? In a broader context, the potential discovery of non-baryonic planets may shift our focus in the search for extraterrestrial life. Historically, scientists have focused on finding planets in the habitable zone, where conditions are suitable for life as we know it. These efforts are grounded in the assumption that life requires certain conditions: liquid water, specific chemical elements, and energy from a nearby star. But non-baryonic planets complicate this model. If planets made of dark matter can exist, then life could potentially exist in ways that we cannot yet conceive. In the search for life beyond Earth, we may need to broaden our criteria beyond traditional habitability and focus on detecting signs of dark matter or other exotic materials that could indicate the presence of life forms entirely different from anything we are familiar with. The implications for space exploration are equally profound. For decades, scientists have focused on discovering exoplanets that share characteristics with Earth, planets that orbit stars within a specific range of temperatures and conditions. These planets are considered potentially habitable. However, if non-baryonic planets exist, this search will need to expand into the realm of dark matter. New detection methods will need to be developed to identify dark matter signatures in distant regions of space, potentially revealing entire populations of rogue planets, many of which may be completely invisible to current observational techniques. This shift could alter how we approach space exploration, pushing humanity to think beyond the familiar and into the unknown. Furthermore, the discovery of non-baryonic planets might help us make sense of the broader dark matter puzzle. For years, scientists have been trying to understand the nature of dark matter. They know that it constitutes about 85% of the universe's mass, yet they cannot detect it directly. One of the most promising candidates for dark matter is the hypothetical weakly interacting massive particle, WIMP, a particle that interacts very weakly with normal matter. If non-baryonic planets are made of dark matter, they could be composed of these WIMPs or similar particles, providing a direct observational link between dark matter and ordinary matter. By studying the properties of these planets, we might be able to gain insights into the composition and behavior of dark matter, taking us one step closer to unlocking one of the universe's greatest mysteries. The discovery of non-baryonic planets would also raise the possibility of a hidden cosmic ecosystem. If dark matter plays a role in the formation of galaxies and planetary systems, it's conceivable that there could be ecosystems operating entirely in the dark matter realm, with non-baryonic planets serving as the homes to unknown life forms. These life forms might not rely on the same physical principles as life on Earth, such as carbon-based chemistry or water-based biology. Instead, they could use dark matter in some way that we do not yet understand, perhaps drawing energy from dark energy or other exotic forms of radiation. If this is the case, then the discovery of non-baryonic planets might be only the first step in uncovering a completely new domain of life and energy, one that exists alongside the visible, baryonic universe. As we continue to search for these planets, there are many questions that remain unanswered. How would a non-baryonic planet form? What conditions are required for the creation of such a planet? Could these planets have moons or companions that are also made of dark matter? Could they interact with other celestial objects in ways that we currently don't expect? And if non-baryonic planets do exist, could they have been around since the early universe, possibly providing clues about the formation of galaxies and the evolution of cosmic structures? One of the key challenges in studying these objects is that we currently lack the technology and observational techniques to detect them directly. For instance, gravitational lensing, when the gravitational field of a massive object bends the light from a more distant object, could be used to detect the presence of non-baryonic planets. However, this technique requires precise measurements and sophisticated equipment, And it's unlikely that we would be able to detect such planets in the near future with our current telescopes and instruments. Despite these obstacles, scientists are optimistic that new technologies, such as advanced gravitational wave detectors, more sensitive radio telescopes, and next-generation space observatories, could one day reveal the existence of these elusive objects. The discovery of non-baryonic planets would be a game-changer, not just for astrophysics but for humanity's understanding of the universe itself. The existence of these planets would challenge our fundamental assumptions about the nature of matter, energy, and life. It would push the boundaries of science, forcing us to confront the reality that the universe is far more complex and mysterious than we could have ever imagined. With every step forward in our search for non-baryonic planets, we move closer to unlocking the secrets of the cosmos and understanding our place within it. The possible existence of non-baryonic planets also pushes us to reconsider how we define a planet. Traditionally, a planet is classified as a celestial body that orbits a star, is spherical in shape, and has cleared its orbit of other debris. However, if non-baryonic planets exist, this definition would need to be expanded. These planets could potentially exist without a star and might not fit neatly into our current criteria. They could possess properties that make them fundamentally different from anything we've previously encountered, raising the question, what makes a planet in the first place? Does it really have to orbit a star to qualify, or could other criteria be more important, such as the formation process or the presence of dark matter? In essence, the discovery of non-baryonic planets would require us to rethink the entire classification system of celestial bodies. These planets might not have atmospheres as we understand them, or they could be made up of exotic materials entirely different from the rocky or gaseous compositions we are familiar with. Imagine a planet with a surface that interacts with dark matter instead of ordinary matter, or a planet composed entirely of antimatter. These are concepts that currently lie at the far reaches of our imagination. But with the right evidence, they could become a reality, forcing us to develop new systems of classification for these unusual objects. As scientists probe deeper into the realm of dark matter, it's possible that we will discover more exotic objects that are composed entirely of non-baryonic matter. These could include moons, asteroid-like bodies, or even entire star systems that exist in a dark matter state. These discoveries would further challenge our understanding of the structure and composition of the universe. If these dark matter bodies have distinct gravitational and electromagnetic signatures, it would signal that there are far more layers to the universe than we previously understood. This could reshape our entire understanding of cosmology, opening up entirely new avenues for scientific inquiry. On a philosophical level, the existence of non-baryonic planets forces us to rethink our place in the universe. For centuries, we have looked to the stars for answers about our origins and purpose. Now, if planets made of dark matter exist, it could mean that life, as we understand it, is not the only possible form of existence in the cosmos. In a sense, non-baryonic planets open up the possibility of other forms of consciousness, intelligence, and even life that are based on principles entirely different from those that govern Earth's biosphere. This realization could expand our horizons, making us rethink everything from the definition of life itself to our approach to searching for intelligent civilizations beyond Earth. It's also worth noting that the discovery of non-baryonic planets could have profound implications for the search for extraterrestrial life. If these planets are found to have any form of life, it would completely alter our understanding of biology. Instead of focusing solely on carbon-based life forms, scientists would need to expand their search for life to include exotic life forms that may not rely on traditional biochemical processes. Such life forms could exist in environments that are completely inhospitable to us, thriving in the absence of light, water, or even stable atomic structures. The implications for biology and astrobiology would be vast, as researchers would need to rethink what constitutes a habitable environment. In this regard, the discovery of non-baryonic planets could serve as a catalyst for a revolution in our understanding of life itself. If life can exist on these planets, it may not be based on the same principles that we know on Earth. Instead of relying on DNA and the complex proteins that form life on Earth, these planets could harbor entirely new forms of life that operate in ways we can't yet comprehend. As we develop new technologies for detecting these planets and analyzing their potential for habitability, we may find ourselves confronted with the possibility of life that challenges everything we know about biology. Another aspect of the non-baryonic planet mystery is their relationship to the early universe. Dark matter is believed to have played a significant role in the formation of galaxies and large-scale cosmic structures. If non-baryonic planets exist, it's possible that they are remnants of the early universe, objects that formed when dark matter began to coalesce in the primordial soup of the cosmos. These planets could provide a unique window into the conditions that existed shortly after the Big Bang, offering clues about how the universe evolved and how the fundamental forces of nature came together to form the structures we see today. Studying these planets could help us unlock the secrets of dark matter and its role in the formation of the universe, giving us insights into the very fabric of reality. Furthermore, non-baryonic planets could shed light on the nature of cosmic evolution itself. Over time, stars burn out and galaxies evolve, but the influence of dark matter persists. If non-baryonic planets exist, they could be a direct link between the evolution of galaxies and the behavior of dark matter. These planets might offer clues about how dark matter interacts with ordinary matter, and how the two have shaped the universe as a whole. This could lead to a deeper understanding of cosmology, one that incorporates not just baryonic matter but also the invisible, yet dominant, dark matter that makes up much of the universe. The potential of non-baryonic planets could also have practical applications here on Earth. If scientists learn to detect and study these planets, they may uncover new principles of physics, energy, or even materials science. These discoveries could lead to breakthroughs that impact everything from energy generation to computing. Understanding how dark matter behaves, or how planets composed of dark matter interact with other celestial bodies, could reveal entirely new avenues for technological advancement. For example, understanding the properties of dark matter could help scientists develop new types of materials that are more efficient or have properties we can't yet imagine. In this sense, the study of non-baryonic planets could become a key driver of future scientific and technological innovation. As the search for non-baryonic planets continues, scientists face the daunting task of developing the tools and technologies necessary to detect these elusive objects. Current telescopes and observatories are not capable of detecting dark matter directly, so researchers must rely on indirect methods, such as gravitational lensing or the effects of dark matter on the rotation of galaxies. However, as technology advances, new techniques could be developed that make it easier to detect these hidden worlds. For example, new types of radio telescopes could be built that are specifically designed to detect signals from dark matter or exotic forms of radiation. Additionally, future space missions could be launched to explore regions of the universe where non-baryonic planets are most likely to exist, providing direct observations and data that could confirm their presence. In the long run, the discovery of non-baryonic planets could be one of the most important scientific breakthroughs in human history. These planets would not only provide insights into dark matter and the early universe but also redefine our understanding of what is possible in the cosmos. If life can exist on non-baryonic planets, it would open up new frontiers in the search for extraterrestrial life, forcing us to reconsider what it means to be alive and what forms of existence may be out there waiting to be discovered. The potential for non-baryonic planets is a reminder of the vastness of the universe and the limits of our current understanding. It forces us to confront the reality that the universe may be far stranger, more complex, and more mysterious than we could have ever imagined. As our technology advances and our understanding of the cosmos grows, we may one day look back on this moment as the beginning of a new era in space exploration, an era in which the mysteries of dark matter, dark energy, and the true nature of the universe are revealed in all their awe-inspiring complexity. The quest to understand non-baryonic planets, however, is far from straightforward. One of the primary challenges is the detection of dark matter itself. While scientists know that dark matter exists, its properties remain largely elusive. Unlike ordinary matter, which interacts with electromagnetic radiation, light, for instance, dark matter does not emit, absorb, or reflect light in any detectable way. This makes it incredibly difficult to study using traditional methods like optical telescopes or space probes. Most of our knowledge of dark matter comes from its gravitational effects on visible matter, such as the way galaxies rotate or how galaxy clusters behave. This reliance on indirect methods to detect dark matter means that the search for non-baryonic planets involves a lot of guesswork and sophisticated theoretical models. For example, scientists might look for anomalies in the motion of known celestial bodies. If a planet made of non-baryonic matter were in orbit around a star, its gravitational pull could cause tiny disturbances in the orbits of nearby stars or planets. Detecting these changes would be incredibly challenging, but not impossible with the right tools. Furthermore, astronomers might need to develop new ways to observe the cosmic microwave background radiation, CMB, for signatures of dark matter. The CMB is the afterglow of the Big Bang, and it carries valuable information about the early universe. If dark matter played a role in the formation of galaxies, stars, and planets, it might have left its mark on the CMB. By studying these tiny fluctuations, scientists could gain insight into the presence of non-baryonic planets and other dark matter structures that have been hidden from view. Another promising avenue for discovering non-baryonic planets is the study of gravitational waves. These ripples in spacetime, first detected in 2015, are caused by the acceleration of massive objects. As gravitational wave observatories like LIGO and Virgo improve, they may be able to detect the faint signatures of non-baryonic planets moving through space. The key would be to identify gravitational waves that do not originate from typical sources, such as black hole mergers, but from more exotic objects composed of dark matter. If such waves could be detected, it would provide another piece of the puzzle in the search for these elusive planets. In addition to the technological and observational challenges, there are also theoretical obstacles to overcome. The existence of non-baryonic planets hinges on our understanding of dark matter and how it interacts with other forms of matter. One hypothesis is that dark matter could form dense objects that behave in ways similar to ordinary planets. These could be composed of exotic particles, such as weakly interacting massive particles, WIMPs, or axions, which would have a gravitational effect on surrounding objects but would be invisible to traditional observational tools. These objects could, in theory, form planets if the right conditions are met, such as a stable region of space where dark matter accumulates. Another possibility is that non-baryonic planets could form from primordial black holes. These black holes, which are thought to have formed in the early universe, could serve as dense cores around which dark matter accumulates. If such objects exist, they might resemble planets in their size, shape, and mass, but their composition would be radically different. These hypothetical dark matter planets could orbit around stars or even exist in isolation in deep space. The challenge here would be to distinguish these dark objects from regular black holes or other dense celestial bodies. The discovery of non-baryonic planets could also have profound implications for the future of space exploration. If these planets are out there, they represent entirely new environments that could hold unknown resources, conditions, or even forms of life. In the search for resources beyond Earth, non-baryonic planets could hold the key to new energy sources, minerals, or compounds that we have yet to discover. Furthermore, if these planets are capable of sustaining life, they would expand the possibilities for colonization and exploration in the far future. One of the most exciting possibilities that comes with the discovery of non-baryonic planets is the idea that they could harbor alien civilizations. While it might seem far-fetched, the concept of life thriving on a planet composed entirely of dark matter opens up entirely new avenues for thinking about what constitutes a habitable world. If life can emerge in such an environment, it might not rely on the same principles of chemistry and biology that we are familiar with. Life might thrive in extreme conditions, relying on entirely different processes for energy and survival. Such a discovery would challenge our assumptions about the nature of life itself. It could redefine what we consider alive and force us to broaden our understanding of biology. We may even need to create new theories of consciousness and intelligence to account for life forms that exist on these strange, non-baryonic worlds. The discovery of non-baryonic life could shift the focus of astrobiology entirely, opening the door to a new era of research into alien life and potentially even contact with extraterrestrial civilizations. In addition to the biological implications, the discovery of non-baryonic planets could also have a profound impact on our understanding of the formation and evolution of the universe. Currently, we believe that galaxies and stars form from the gravitational collapse of ordinary matter. However, if dark matter plays a larger role in the formation of celestial bodies than we currently understand, it could force us to rethink the entire process of cosmic evolution. Non-baryonic planets could represent a fundamental component of the universe's makeup, and by studying them, we could uncover new insights into how the universe began, how it has evolved, and how it might continue to change in the future. Moreover, these planets could help resolve some of the greatest mysteries in cosmology. For example, dark matter is believed to make up about 27% of the universe's mass, yet it remains invisible and undetectable except for its gravitational effects. Non-baryonic planets could provide a unique opportunity to study dark matter in more detail, offering clues about its nature, its properties, and how it interacts with ordinary matter. This could ultimately lead to breakthroughs in physics, giving us a deeper understanding of the fundamental forces that govern the universe. In the grand scheme of things, the discovery of non-baryonic planets would be a pivotal moment in the history of science. It would not only expand our knowledge of the universe but also change the way we view our place in it. As we continue to explore the cosmos and develop new technologies for detecting dark matter, we may one day uncover the existence of these hidden worlds. When that day comes, it will be a testament to the ingenuity and perseverance of humanity's quest for knowledge and understanding. The discovery of non-baryonic planets would mark a monumental shift in our understanding of the universe. As scientists venture deeper into the mysteries of dark matter, the implications of finding such planets would reach far beyond just cosmology. It would have consequences for everything from the future of space exploration to our understanding of the very fabric of reality. The study of non-baryonic planets could eventually shed light on how the universe was shaped, what forces govern its expansion, and perhaps even offer insights into the nature of life itself. At present, we know that non-baryonic matter, primarily in the form of dark matter, makes up a large portion of the universe's mass. Yet, its true nature continues to elude us. If non-baryonic planets exist, these objects could serve as some of the most important test subjects for theories about dark matter. By observing their gravitational influence, their effects on surrounding celestial bodies, or any potential emissions of energy they might produce, albeit in a form that we do not yet fully understand, scientists could refine their models of the cosmos. Dark matter, unlike baryonic matter, the matter we are familiar with, does not interact with electromagnetic forces, meaning it doesn't absorb, emit, or reflect light. This lack of interaction with light has made studying dark matter extremely challenging. It's theorized that dark matter is primarily composed of weakly interacting massive particles, WIMPs, axions, or other exotic particles that do not conform to the properties of the particles that make up ordinary matter. But the exact composition remains speculative. What is clear is that dark matter exerts a gravitational pull on ordinary matter, and it appears to play a crucial role in the formation of structures in the universe, such as galaxies and galaxy clusters. This gravitational influence is a critical piece of the puzzle, suggesting that the universe's mass and energy composition might be far different from what we perceive. If non-baryonic planets are indeed out there, they would likely be composed of dark matter in some form and would provide a new and unprecedented opportunity to study this mysterious substance. The notion of non-baryonic planets is a compelling one because it fundamentally challenges our view of what a planet can be. Our traditional understanding of planets is based on the idea that they are composed of baryonic matter, atoms made up of protons, neutrons, and electrons. But if dark matter can accumulate in sufficient amounts, it might form gravitationally bound structures that mimic the behavior of planets. These structures could range from small, rocky-like objects to large, gas giant-like bodies that are dominated by dark matter. Such a paradigm shift would force us to reconsider what we believe constitutes a habitable environment. If planets composed primarily of dark matter can form and sustain themselves in the same way as traditional planets, then there could be possibilities for the existence of life forms that operate according to entirely different principles. Imagine a form of life that interacts with dark matter or that could harness the unique properties of non-baryonic matter for its energy processes. This would open up a whole new chapter in astrobiology and challenge everything we know about how life might emerge in the universe. The gravitational effects of non-baryonic planets could offer some of the most tangible evidence of their existence. In the current paradigm, astronomers rely on methods such as gravitational lensing, where the gravity of an object distorts the light from more distant sources, to detect unseen objects like dark matter. If non-baryonic planets are present in the cosmos, their gravitational influence on nearby stars and galaxies might be detectable through similar techniques. These planets could cause subtle distortions in the motion of nearby celestial bodies, potentially signaling their presence in otherwise unnoticed ways. One of the more speculative but fascinating ideas is that non-baryonic planets could exist in regions of space that we have yet to fully explore, far beyond the reaches of our current telescopic capabilities. These planets might not be in close proximity to any stars and could exist in isolation, drifting through intergalactic space where their gravitational effects would be less likely to be noticed. Or they could be part of dark matter clumps within galaxy clusters, where the gravitational pull of these planets would be masked by the larger mass of dark matter in the region. Finding such planets could be incredibly challenging, but not impossible. The study of dark matter, and by extension, non-baryonic planets, could offer significant insights into the early stages of the universe. Dark matter is believed to have played a crucial role in the formation of the first galaxies and stars. It's possible that the gravitational influence of dark matter helped clump ordinary matter together, providing the seeds for galaxy formation. If non-baryonic planets exist, they could offer a glimpse into the conditions that existed in the universe's infancy, helping scientists understand how structures formed and evolved over cosmic timescales. At the same time, non-baryonic planets could reveal a great deal about the large-scale structure of the universe. Their distribution and behavior might give clues to the nature of dark matter and how it has influenced the formation of cosmic structures like galaxy clusters, superclusters, and voids. Understanding where these planets exist and how they interact with surrounding matter could potentially help us map the vast cosmic web of dark matter and its impact on the evolution of the universe. As the search for non-baryonic planets continues, new technologies will likely emerge that could make such discoveries more likely. For instance, advances in gravitational wave astronomy could provide a new way to detect dark matter structures and objects that are otherwise invisible to conventional observation methods. The detection of gravitational waves from non-baryonic planets could offer direct evidence of their existence. Additionally, improving techniques for studying the cosmic microwave background radiation could help scientists detect signatures of dark matter in the early universe, possibly linking it to the formation of planets composed of non-baryonic material. The discovery of non-baryonic planets would also open up new possibilities for space exploration. Although these planets would be vastly different from anything we know, the sheer diversity of celestial bodies in the universe suggests that there are untapped resources, environments, and phenomena awaiting discovery. Non-baryonic planets, though enigmatic, could harbor novel energy sources or even serve as platforms for future exploration. Another intriguing possibility is that these planets could act as stepping stones in the search for extraterrestrial life. If planets composed of dark matter exist, and if they somehow provide the right conditions for life, they could be entirely different from anything we've imagined. The life forms on these planets might harness the unique properties of dark matter, leading to entirely new forms of biology that defy our current understanding. As the search for non-baryonic planets continues, it is possible that new scientific paradigms will emerge, dramatically shifting our view of the cosmos. The mysteries of dark matter and non-baryonic planets could help us unlock fundamental secrets about the universe's formation, evolution, and ultimate fate. Understanding these dark worlds might not only transform our knowledge of the universe but could fundamentally change our place in it. The quest to understand non-baryonic planets is one that challenges our very conception of what a planet can be. These hypothetical worlds, composed of dark matter, could be unlike anything we've ever encountered. As the search for these elusive objects continues, we are bound to uncover groundbreaking revelations that will shape our understanding of the cosmos for generations to come. As the search for non-baryonic planets progresses, the growing advancements in technology and theoretical physics may push the boundaries of what we can comprehend about these exotic celestial bodies. Each new discovery in the realm of dark matter brings us one step closer to understanding whether these hypothetical planets could actually exist in the universe. But even if we do manage to detect a non-baryonic planet, the implications of such a discovery would stretch far beyond merely confirming the presence of dark matter in a new form. Non-baryonic planets could potentially serve as a key to unraveling the deepest mysteries of the universe. One of the most profound questions in cosmology is the origin of dark matter. While its gravitational effects are observable in galaxies and galaxy clusters, we have yet to directly detect dark matter particles. If non-baryonic planets exist, they could act as a natural laboratory for studying dark matter in a way that we never thought possible. By analyzing the gravitational influence of a non-baryonic planet, scientists could attempt to infer the properties of dark matter particles. For instance, if these planets interact with normal matter in a subtle way, perhaps through the weak nuclear force or through some other unknown interaction, we might detect that interaction as a faint energy signature or by observing perturbations in the surrounding stellar systems. It could provide a glimpse into the nature of dark matter that could not be achieved through traditional means of particle physics experiments. Furthermore, the study of non-baryonic planets could have profound implications for our understanding of the fundamental forces of nature. At present, our knowledge of gravity, electromagnetism, the strong force, and the weak force stems largely from our study of baryonic matter. But the potential existence of non-baryonic planets would force scientists to consider how these fundamental forces operate in the presence of dark matter. This could lead to the development of new theoretical models that extend our understanding of physics and help bridge the gap between general relativity and quantum mechanics. Interestingly, non-baryonic planets might also challenge our understanding of planetary formation. Current models suggest that planets form from the collapse of gas and dust around a central star, with gravity pulling matter together into a dense core. But how would this process unfold in a universe where dark matter plays such a significant role? If non-baryonic planets exist, they may not form in the same way as the rocky or gaseous planets we are familiar with. Instead, their formation might involve entirely different processes, driven by the behavior of dark matter and its interactions with other forms of matter. This presents another exciting possibility: the potential for non-baryonic planetary systems. While we traditionally think of planets orbiting stars, the discovery of non-baryonic planets could suggest that they may form and exist in isolation or within different types of star systems. Imagine entire systems of planets, bound together not by the gravitational pull of a star but by the influence of dark matter. Such systems would challenge our traditional models of how planets interact and how life-supporting environments are shaped. As we probe deeper into the universe, the potential existence of non-baryonic planets could also affect the search for extraterrestrial life. If life can exist on a planet composed largely of dark matter, the conditions necessary for life as we know it would be vastly different from those found on Earth. The environments on these planets might be extreme, perhaps with extremely low temperatures or unusual atmospheric conditions. Yet, this could open the door to new forms of biology that don't rely on the same chemical processes we associate with life on Earth. It's also worth considering that non-baryonic planets might be located in regions of space that are difficult for us to observe with current technology. Dark matter does not emit light, so detecting objects composed of dark matter presents unique challenges. These planets might be hidden in plain sight, blending seamlessly with the dark matter that permeates the universe. The only way to detect them might be through their gravitational effects on surrounding objects, such as the bending of light from distant stars or the motion of nearby celestial bodies. In fact, the discovery of non-baryonic planets could prompt a re-evaluation of how we conduct space exploration. If these planets are located in regions where light is scarce or impossible to detect, scientists would need to develop new techniques to study them. This might involve improving our ability to observe gravitational effects, perhaps by enhancing the sensitivity of telescopes or developing entirely new types of observational equipment that can detect the subtle influence of dark matter. One of the more exciting possibilities is the role non-baryonic planets might play in the future of interstellar travel. In the distant future, these planets could act as hubs or waypoints for humanity's deep space missions. If these planets harbor unique resources or offer valuable gravitational properties, they might become important destinations for spacecraft traveling through the galaxy. The study of non-baryonic planets could not only enrich our understanding of the universe but also guide future human exploration and settlement. The notion of non-baryonic planets is still theoretical, but the mere suggestion that such objects could exist challenges everything we know about the cosmos. It forces us to ask fundamental questions about the nature of matter and the forces that govern the universe. Whether or not these planets are eventually discovered, the search for them will drive advancements in physics, astronomy, and technology. It will push the boundaries of scientific inquiry and challenge our understanding of the very building blocks of the universe. In a sense, the quest for non-baryonic planets is not just about discovering new worlds. It's about discovering a new way of thinking about the universe. It's about reimagining what is possible and expanding the horizons of human knowledge. Whether these planets are eventually found or not, the pursuit of their discovery will inspire generations of scientists and explorers to reach for the stars and seek answers to the greatest mysteries of existence. As we continue to study dark matter, explore the far reaches of the universe, and develop new technologies to observe the unobservable, the dream of discovering non-baryonic planets may one day become a reality. If and when that day comes, it will represent one of the most profound moments in the history of science, a moment that will change our understanding of the universe and our place within it forever. The ongoing search for non-baryonic planets will undoubtedly push the limits of our understanding, but it will also spark a wave of new questions about how we define the nature of planets, matter, and life itself. For centuries, we've had a well-established notion of what constitutes a planet, something that is composed of atoms, whether rocky or gaseous, held together by gravity. But what happens when that definition is challenged by the existence of a planet made primarily of non-baryonic matter, such as dark matter? Such a discovery would force scientists to reassess not only the physical makeup of planets, but also how they interact with the universe around them. Imagine a planet that doesn't behave like anything we know, one that doesn't reflect light, one that doesn't have the typical chemical processes that sustain life as we know it. What would it mean for our search for extraterrestrial life? Would it expand the possibilities of what could be considered life-supporting environments, or would it introduce a new kind of life, one based not on ordinary atoms, but on dark matter or other exotic particles? The mere idea of a non-baryonic planet adds a layer of complexity to our already complex understanding of space. Scientists will need to develop entirely new frameworks for thinking about how these planets fit into the grand cosmic puzzle. While gravitational interactions can give us some clues about their presence, how else could we study such strange worlds? Standard telescopes, which rely on detecting light and electromagnetic radiation, would struggle to capture any data about non-baryonic planets, since dark matter doesn't interact with light in the same way that normal matter does. Perhaps we would need to develop new, more sophisticated methods of observation. One possible approach could involve the detection of gravitational waves or the bending of light around these objects. Gravitational lensing, where light from distant stars or galaxies is bent by the gravitational field of an object, could be used to uncover the presence of a non-baryonic planet. However, the challenge would lie in isolating this effect from the countless other sources of gravitational waves in the universe. It would take careful, precision-based instruments to detect even the faintest traces of a non-baryonic planet. Another exciting avenue of research could involve studying the interactions between non-baryonic planets and their surrounding environments. While these planets might not be able to interact with light in the way that ordinary planets do, they could still exert subtle effects on nearby matter, such as stars, asteroids, or other celestial bodies. These interactions might offer clues as to the nature of dark matter and how it behaves on a larger scale. Researchers might observe shifts in the orbits of nearby stars, changes in the motion of neighboring planets, or even the emission of strange particles that can be traced back to these hypothetical planets. The potential implications for our understanding of dark matter and the fundamental forces of the universe are vast. For years, physicists have been theorizing that dark matter exists, and yet it has remained elusive. If non-baryonic planets can be discovered and studied, they could provide a breakthrough in our understanding of this mysterious substance. If dark matter truly composes a significant portion of the universe, then learning how to detect and understand it through non-baryonic planets could be a key milestone in unraveling one of the most profound mysteries in science. The pursuit of non-baryonic planets could also lead to new insights into the origins of the universe itself. The Big Bang Theory proposes that the universe began as a singularity, a point of infinite density, and then expanded rapidly, creating all the matter and energy we see today. However, this theory doesn't explain the mysterious origins of dark matter. Were non-baryonic planets formed in the early moments of the universe, or did they arise later through some other cosmic process? Answering these questions could reshape our understanding of the universe's birth and its eventual fate. Moreover, the discovery of non-baryonic planets could alter our search for habitable worlds. Today, astronomers search for exoplanets that resemble Earth, planets with the right temperature, atmosphere, and chemical composition to support life. But if non-baryonic planets exist, then our criteria for habitable worlds would need to be re-evaluated. Could there be a type of life that thrives on dark matter? Could a planet composed primarily of dark matter offer the right environment for a completely different form of biology? This would be a paradigm shift in astrobiology, challenging our most basic assumptions about what life is and where it can exist. In practical terms, the discovery of non-baryonic planets might also lead to new opportunities for exploration. While these planets would be difficult to study from a distance, they could become important targets for future space missions. As technology advances, it may become possible to send probes or even manned missions to explore these strange worlds. These missions would likely focus on studying the gravitational interactions between these planets and their environments, seeking to learn more about dark matter and its role in the cosmos. On the technological front, the search for non-baryonic planets could inspire innovations in space instrumentation and computational methods. Understanding the behavior of dark matter and developing ways to detect its effects would require advancements in both hardware and software. We might see new types of sensors capable of measuring gravitational anomalies or sophisticated algorithms designed to sift through massive datasets in search of subtle, dark matter-induced patterns. In the same way that the search for exoplanets has led to breakthroughs in astrophysics, the search for non-baryonic planets could spark a new wave of technological advancements. The concept of non-baryonic planets is one that challenges our fundamental understanding of the universe. While these planets remain hypothetical, the implications of their existence would be nothing short of revolutionary. From redefining the nature of matter and the forces that govern the universe to opening up entirely new avenues for space exploration and astrobiology, non-baryonic planets could reshape our perception of the cosmos in ways we can only begin to imagine. The search for these enigmatic worlds is far from over, and whether or not we eventually find them, their potential to unlock the secrets of dark matter and the very nature of existence is an exciting prospect that will continue to fuel scientific inquiry for generations to come. The exploration of non-baryonic planets is more than just a quest to discover new worlds. It is an opportunity to radically reshape our understanding of physics, the cosmos, and the very fabric of reality itself. As we continue to look toward the future of astrophysics, the study of such hypothetical planets will challenge not only our technological capabilities, but also the fundamental principles of science that we hold dear. Consider the implications of finding a non-baryonic planet that defies all the conventional rules of matter and energy. Scientists would need to rethink everything, from the basic structure of planets to the definition of what constitutes a habitable world. It could force a reevaluation of our understanding of gravity, electromagnetic forces, and even quantum mechanics. In fact, the discovery of such a planet could offer profound clues to the unification of the four fundamental forces of nature: gravity, electromagnetism, the strong force, and the weak force. Take gravity, for instance. Gravity is the one force that acts on all matter in the universe, whether it's ordinary baryonic matter or dark matter. But the interaction of dark matter with gravity is still not fully understood. If we discovered a non-baryonic planet, scientists would have a unique opportunity to study how dark matter behaves in such environments, and how it influences other objects in the solar system. This could lead to new insights into gravity's role in shaping the structure of the universe, potentially offering clues to the long-standing puzzle of why gravity is so much weaker than the other fundamental forces. Furthermore, the discovery of non-baryonic planets might prompt scientists to revisit existing theories about the formation of planetary systems. Current models of planet formation involve the accumulation of dust and gas around a central star, with matter eventually coalescing to form solid planets. However, this process relies on the assumption that the matter involved is composed of normal baryonic particles. What happens, though, if a planet is composed primarily of non-baryonic material? How would such a planet form, and what factors would contribute to its creation? The implications of non-baryonic planets also extend to our search for life beyond Earth. Currently, we define life in terms of biological processes that depend on carbon-based molecules, water, and other familiar elements. However, the existence of planets made primarily of dark matter or other exotic particles raises the question: could life exist in entirely different forms, based on particles and forces that we don't fully understand? Imagine a world where life could not be detected by our traditional methods, but instead relied on interactions that are completely foreign to us. Could there be a form of life that exists in symbiosis with dark matter, or perhaps even feeds off the exotic particles that make up these non-baryonic planets? Such possibilities would fundamentally alter the way we think about astrobiology. The search for alien life would no longer be confined to the search for planets with liquid water and familiar chemical compounds. Instead, scientists would need to expand their criteria for what constitutes a life-sustaining environment, taking into account planets that are made of materials that are entirely different from anything we've encountered. This could lead to the discovery of entirely new forms of life, which would redefine our understanding of what it means to be alive and how life could potentially thrive in the universe. In addition to these philosophical and scientific questions, the discovery of non-baryonic planets could have practical implications for future space missions. If these planets exist, they might be located in regions of space that are difficult to reach with current technology. Exploring such distant and unknown worlds would require the development of new spacecraft, propulsion systems, and navigation techniques. Future space missions might need to be equipped with entirely new tools to detect the subtle signs of non-baryonic matter, such as changes in gravitational fields or unique particle emissions. One of the biggest challenges would be determining how to communicate with or study these planets without the usual electromagnetic signals we rely on for observation. Since non-baryonic matter does not interact with light in the same way as baryonic matter, astronomers would have to develop new methods of probing these objects. This could involve harnessing different parts of the electromagnetic spectrum or utilizing indirect methods, such as observing the gravitational effects these planets have on nearby stars or galaxies. These innovations would undoubtedly push the boundaries of technology and require the collaboration of physicists, engineers, and computer scientists. Looking further ahead, the discovery of non-baryonic planets could open up entirely new avenues for space exploration. It is possible that non-baryonic matter could be harnessed in some way for advanced technologies. For instance, dark matter is thought to make up a large portion of the universe's mass, yet it interacts with ordinary matter so weakly that it is incredibly difficult to detect. If scientists could find a way to interact with dark matter, it could lead to breakthroughs in energy production, propulsion systems, or even quantum computing. Imagine harnessing dark matter as a fuel source for interstellar travel, or using its unique properties to create new materials with extraordinary capabilities. Moreover, these discoveries could spark an entirely new era of space colonization. Just as we have begun to explore the possibility of establishing human settlements on Mars, the discovery of non-baryonic planets might lead to the idea that life could exist in conditions that we had previously thought inhospitable. It's a tantalizing prospect. Could we one day colonize a world made entirely of dark matter, or even use such a planet as a base for further exploration into the cosmos? Of course, all of these ideas remain speculative at this point, as non-baryonic planets are still a hypothetical concept. However, the very thought of their existence forces us to reconsider everything we know about the universe. It's a reminder of how much we have yet to learn and how much potential there is for discovery in the uncharted territories of space. As we continue to search for these elusive planets, we will undoubtedly face numerous challenges. Our current technology may not be up to the task of detecting or studying non-baryonic planets in detail, but the very pursuit of this knowledge will drive innovation and discovery in ways that we cannot yet imagine. In the end, the search for non-baryonic planets could be one of the most exciting and transformative journeys humanity has ever undertaken. It could reveal not only the hidden nature of the universe but also the potential for new scientific paradigms that will shape our understanding of reality for centuries to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.